Nope, I just realized I have my sound muted. So sorry if anybody was asking questions. Apparently I had my sound muted. You guys can hear me though, right?
Yes.
Okay,
Yes, we
excellent. And I can hear you too. Perfect. Excellent. All right. So, okay, today is Monday, November 23rd. And for the first time so far, we've got our entire rest of our schedule here on the board. But before we get to that, I do want to talk about the exam as we were mentioning. I am very pleased with the results of this exam, some definitely improvement, and especially in the lecture exam. I know that there was a lot of material in the lab exam, but still we had one of our highest averages for this one, and I was very pleased with that. But what I was really excited to see was the improvement on the lecture exams. The scores on the lecture exams have gone up significantly. And again, you got a lot more people are being a lot better about being descriptive in describing the things that they are talking about and the important concepts and the minutia of detail that helps you to be successful. So I was very, very pleased with that. Like last time, I will be releasing the exams after class today, and then you'll have the next day to look over your questions and answers. And if you have any questions, you can contact me about that. And the overall grade is, again, creeping up significantly as well. We still have a fair amount to do. And remember also, as we talked about, that final exam counts as a score and also can replace your lowest lecture score. So there is still some opportunities for some big swings in grades for people to improve who are really putting in the time and effort. Let's talk about the things that are remaining. We have today, we're going to talk the physiology of the potentials, and then we're going to get into our histology and our brain anatomy finally. Normally, I don't announce them ahead of time, but again, with it being a holiday week, I did want to make everybody aware that Wednesday we will have a daily quiz at the beginning of class, so 5 for 5. So make sure you are ready and prepared for that, as well as your Unit 13 review is going to be due. Monday, your Physio X exercise 3, which has 9 activities, is going to be due. Also, your cranial nerves, which again is not an assignment you are turning in, but there is a worksheet for that. And as I mentioned, depending on how far we get in the material, the cranial nerves could be as much as 25% of your lab exam. So it's important to know those. So I encourage you to look at them ahead of time, but we will be going over them together on Monday, the 30th. So I think it's important to make sure that you have that handout, or at least I've written something out to help you to go through that material so we can talk about it. And it would be a good thing to look at it ahead of time too, so it's not all new. Wednesday next week, your 15-point nervous review is due, which will be graded for correctness. Again, the key to that, it is looking at the relationship between structure, function, and location. We will start to talk about that today in our lab. And so again, that's why it's not due for a while. And I don't even remember if it's available yet. I don't think it is available yet, because I think it's available today or even Wednesday, because I don't want you working at it yet. You don't know these anatomy structures yet. And so it'd be pointless to start working on them yet. But after the things we start talking about today, then you will start to understand what is expected of you on that. And so then you'll be able to start working on that. Monday, the 7th of December, your last 2 assignments are due. Unit 14 review is due, and then there's going to be a fun reflexes lab that you'll be doing out of your lab manual. Some of the I will worry about putting the sections and the units and the activities when we get closer to that, but it's something that you can do at fun. Gives you an excuse to hit your loved ones with a hammer and stuff like that. And so it will be a fun activity that you will be doing at home. Then Wednesday the 9th, we have our lab and lecture exam, same as it ever was. You know what to expect from that. And then 1 week after that, you have your final exam. So you have a full week. We do not meet on Monday the 14th. That is finals week. So from Wednesday the 9th, we don't, well, actually, I don't see you during the exams anyway. But we will have 1 full week to be able to prepare for the final exam. The final exam is cumulative, covering everything, lab and lecture, that we have covered in this class since the very beginning of class. However, remember, the format for this final exam is going to be 100 multiple choice questions. You are going to have, I think it's like 100 minutes to complete the 100 questions, something along those lines. And again, there are 2 things that you need to remember about multiple choice questions. The first is that the advantage of them is that you have the correct answer there right in front of you. You don't have to pull that piece of information out of the ether. You just have to recognize the correct answer. And that is a very different skill. So that is the big advantage to multiple choice questions. However, remember the big disadvantage to multiple choice questions is multiple choice questions almost by definition are tricky, right? They're worded in such a way where if you misread one word, you are going to misinterpret the question, and they're going to have that trap answer to catch you. So you really need to make sure you're taking your time to read the questions carefully so that you can answer them correctly. I say that for every exam, but it is especially true for this one because it is all multiple choice questions. All right, so the answers, the correct answers are there. You just have to find them. And again, remember, the final exam counts as a grade on its own. So even if you're doing really, really well in this class, you still need to prepare for it and at least be somewhat successful. Again, that's the advantage of banking points. Somebody who's really been banking a lot of points may only need to get a 70 or something like that to maintain their grade, or even less than that. But that's the advantage of banking those points ahead of time. But again, you still want to spend some time. Nobody cannot take the final exam. Everybody needs to take the final exam. But remember, your reward for gaining and retaining this information is you can use that final exam to replace your lowest lecture score. Lecture score, lab scores don't all count. But if you have a lecture score, maybe the first exam score you really struggled with because you weren't prepared, didn't understand what a class like this was needed, maybe the third exam, grandma got married in Vegas or something like that. And again, we can see huge swings. I have people who get 30s on one of their exams because they weren't able to prepare for it properly. And they get an 80 something on the final. And basically that is 50 more points that you are throwing into your bucket. So it can still really help those people that are on the border or really trying to reach that grade that they want. It is something that can help you to get there. All right, so I definitely want to reward you for gaining this information and retaining it, because guess what? I didn't pick the information that I'm teaching you randomly out of the hat. A lot of the stuff that I've been teaching you is stuff you're going to use in 431. Right. And my 431 grumbles all the time about how much stuff they have to use from 430. Right. Guess what? You're not done with a ciliated pseudostratified columnar epithelial tissue. You'll get to play with that when you get into 431 as well. So it is important that you learn and retain this information. All right. Questions on any of that?
I have a question.
Yes.
So it's going to be all multiple choice answers, but there'll still be lab type questions on there.
Yes. So, for instance, something that we haven't seen up to this point of time is you may have a labeled picture with, like, for instance, a cross section through a long bone. And, so it may point at one of the circular rings of matrix that are forming that organizing structure of the compact bone. And it may be what identify the, A or something like that on there. And so you would need to know that that is for instance, concentric lamella. Right. So from the list. So there might be a list of items and then an image or something like that. And I would say probably less than 10, but somewhere around probably 6 to 10 questions, maybe something like that. Again, it's hard for me to say because it's all randomized, but there are questions like that. The other types, so for the most part, so here's what I'll say. The multiple choice questions are not the multiple choice questions you've had on previous exams. Right? The point of this isn't to memorize the questions that I've already asked you in this class. The point of this is to memorize the questions. So it's a whole new subset of multiple choice questions having nothing to do with the ones that you asked before. And remember, everything that's been in an essay question is something that could be a multiple choice question. And remember also, the exams you've taken haven't covered all of the material in the class. Again, the muscle contraction is a perfect example. Every single one of you got at least 2 questions about those 3 processes in the muscle contraction, right? And just because you got excitation contraction coupling and just because you got contractile cycle doesn't mean there aren't going to be any questions on communication at the neuromuscular junction on your exam. So again, that's one of the reasons why I don't leave the exams open. The exams are not a good way to study for the final. Your previous exams are a small subset of information that you were responsible for out of all of the stuff that you're responsible for. So you will definitely see stuff on the final that wasn't on the previous exams. most of the types of multiple choice questions are basic types of multiple choice questions. The two things that will be different is there will be some images that you will need to recognize things from images. So there is some lab representation on there. The other thing that I would say is normally processes, right? If there's a great process, I ask you that as an essay question. So instead, what you may see is the type of questions where you have 5 steps in a process and you have to put them in order. Right, so there'll be 5 steps in the process, and then there'll be 4 options or 5 options of how you put them in the correct order. So those would probably be the two types of the two types of multiple choice questions that you haven't seen up to this period of time, because I've tested you on those things in other ways. But it is important to know the processes. It is important to know some anatomy. Okay. Now, again, does that mean that you need to memorize every single origin insertion for every single muscle we've covered for the final exam? No, I mean, I'm not necessarily going to go into that much detail, but do you need to know, for instance, what bones, for instance, a muscle might connect to? Yeah, I think that was that. And again, I would say that for this final exam, easily 50% of the material should just be aha information we've used so much in this class that it should be aha information. Like, for instance, the sodium potassium ATPase. How much sodium does it move?
Three.
And what direction?
In.
In?
Out.
Out. There you go. How much potassium does it move?
2.
What direction?
And
In, absolutely, right? So, I mean, there's a piece of information like that we've used a lot, and we're going to continue to use a lot more as we move forward in this section. So it should be obvious information. There's more calcium outside the cell. There's more chloride outside the cell, right? All of this kind of stuff. So some of this information should be stuff that we've used enough that it should be pretty obvious when you see it on the exam. All right. All right. Any more questions on any of that? All right, excellent.
We will be able to see the result after the lecture, you said?
Yes, so after the exam today, after the class today, I will release the exams. And then, like I said, as always, you'll have 24 hours to be able to look at them. All right. And remember, I have office hours right after class. I have office hours from 11 to 12 tomorrow. So if you have questions about your exams, those are a perfect time to see me about them. All righty. Let's go ahead then and get started on lecture. All right, so we left off last class and we were talking about equilibrium potentials. We were talking about the driving force of ions, because ions want to be happy. Ions want to be at equilibrium. And what did we say the equilibrium potential of sodium was?
Positive 66.
Positive 66 millivolts, excellent. And what was the equilibrium potential of potassium again?
Negative 90.
Negative 90 millivolts. Excellent. Spectacular. So what happens is when we open a sodium channel, sodium is going to move to try to bring that cell to positive 66 millivolts. If we open a potassium channel, potassium is going to move to try to bring the cell to negative 90 millivolts. They want to be at their equilibrium, and that is all they care about. And so that is going to be their driving force. And that's important because, as we mentioned, when a charged ion, a charged particle, crosses the plasma membrane, basically it produces a current, an electrical current. You have a same way a charged electron moving along a wire lights up your house. Here we have charged particles moving into and out of the cell, producing an electrical current. And we call those electrical currents potentials. Now, as we also talked about, there are 2 types of potentials. What are the 2 types of potentials?
Bursting membrane potential.
True, there is a resting membrane potential, absolutely. But again, if it's resting, then it's really not producing a current, and it doesn't allow us to do work. To do work, we have to change the number of ions that are coming in and out using those gated channels, right? And those produce those two types of currents, those two types of potentials. And what are the two flavors of them?
Graded.
Graded and
Rated in action potential.
different.
graded and action. Excellent, perfect. So let's talk first about a graded potential. Oh, and actually, hold on, let's do one more thing, although I can do this here as well. So we have graded potentials. And what are some of the things that we know about graded potentials? Well, there's a big clue right at the top of the screen right now.
They're small.
There you go, they're small. What else do we know about them?
Occurs along the dendrites and cell bodies.
Excellent. Remember, it only occurs along the dendrites and cell bodies because they don't have that specialized plasma membrane that allows them to produce an action potential. What else do we know about them? There's two other things that we know about them that are important.
They vary in amplitude.
Excellent. They can vary in amplitude. Slightly smaller, slightly bigger, and not only can they vary by getting a little bit smaller and a little bit bigger, but what else do we know about them? Remember, our action potential is a big positive signal, but what do we know about graded potentials?
Positive or negative.
Right, they can be positive or negative. Excellent. These are the things that we know about graded potentials. Spectacular. So, small deviations from the resting membrane potential. They occur in the dendrites and the cell bodies because they don't have the specialized axolemma. They can vary in amplitude, and they can be positive. And as we know, when you go get more positive, then the resting membrane potential, we had a fancy term for that, and that was that it depolarizes. Now we have a second fancy term. If you get more negative than the resting membrane potential, then we say that you hyperpolarize. Exactly. So we have these positive and negative signals. All right, they can be positive, they can be negative, they can be depolarizing, they can be hyperpolarizing, they're going to be small in amplitude. But there's one more trick to this, and for this, let's go back to our whiteboard. So we'll draw our graph here. If we're going to be talking about graded potentials, and again, since we're going to need these anyway, let's go ahead and get started. Give me all of the important numbers we need to know on this graph.
Resting membranes negative 70.
Excellent. Let me move some of these things out of my way so I can play a little bit more. There we go. This is so big. Okay, excellent. So, perfect. First one we need to know is our resting membrane potential. And it is, first that's way too large, so let's make that. Negative 70 millivolts, excellent. What's another important number we need to know?
Minus 60.
And what is that minus 60?
Threshold.
Threshold. Threshold for what?
Action potential.
Okay, true. It is the threshold to action potential, but what actually happens at threshold?
Depolarization.
Well, we have to depolarize to reach threshold, but once we reach threshold, what actually happens? What is the mechanical event?
Calcium channels opens.
Which ones?
The calcium channels.
No, not necessarily calcium channels. What kind of channels open?
Ion channels.
Okay, what kind of ion channels?
Voltage.
Voltage gated.
There we go. is the voltage. This is the threshold for, let's say it that way, for the opening of all voltage-gated channels. You're right, there are voltage-gated calcium channels, but it isn't just voltage-gated calcium channels that open at threshold. All voltage-gated channels open at threshold, and that threshold is -60 millivolts. Excellent. All right, give me another number we need to know.
The sodium and potassium values.
Excellent. And what are the equilibrium potential of sodium?
66.
Positive 66. We do want to
Yep.
be careful about that, but absolutely. Of sodium, which is positive 66 millivolts. Oops. And one more important number.
Potassium.
Potassium's equilibrium potential, which is what?
-90.
Excellent. Spectacular. Those are our 4 important numbers that we absolutely positively need to know. That one there. That one there. That one there. And that one there. Excellent. All righty. So for a graded potential, remember our job is going to be to move the cell off of its resting membrane potential. So again, remember, cells, if left alone, will happily stay at their resting membrane potential forever. But what we need to do is disturb it. We need to disturb it in such a way where we are going to be able to get, oops, hold on, use that one. Either a small increase in membrane potential. And what would we call that small increase in membrane potential?
Depolarization.
Depolarization. Of course, as we know, these depolarizations typically don't last for very long. And so while it may depolarize for a short period of time, it is going to go back to rest. And what do we call that process of going back to rest?
Repolarization.
Excellent. Repolarization. Spectacular. Conversely, oh, and so let's do one more thing. What type of channel would you open to depolarize it?
Voltage-gated calcium channels.
Well, let's start with, okay, so calcium is a good option. Calcium is a positive ion that wants to come into the cell. But what do we know about calcium when it comes into the cell?
Makes it do wonky things.
Makes it do wonky things, and we don't necessarily want cells to do wonky things all the time. So calcium's probably not going to be the primary ion we're going to want to use for a graded potential. So what's
Sodium.
Sodium, absolutely, because sodium, remember, is going to want to come in and make the cell more positive. Excellent. All right. Now, the next question is, we mentioned sodium channel, but remember this has to be a gated channel. One of the key things with a graded potential is these graded potentials can be a little bit smaller or they can be a little bit bigger. We can vary them in amplitude. If our goal is to make the amount smaller and bigger, what types of sodium channels, what type of gated channels might we want to use to produce this graded potential?
Selective.
Well, okay, true. All gated channels are selective. Let's work our way back. There
Voltage
are
or chemical?
Say again?
Voltage or chemical gated?
Okay, excellent. So we have voltage gated, we have chemically gated. What was the third type? Well, but see, remember, leak channels can't be open and closed, so they're not going to help us to do work. So let's start listing this. We have voltage gated. You guys said chemically gated.
Mechanically.
Mechanically gated. Excellent. So there are three possible types of channels. So if we want to produce a variable system, what kind of ones do you think we'll be able to use for this? Would voltage gated work? No, exactly. Remember, voltage gated have a threshold. Below threshold, how many of our voltage gated channels are open? 0. Above threshold, how many of your voltage gated channels are opened?
All of them.
All of them, right? So is there any way to open up just half of the voltage gated channels or a quarter of the voltage gated channels to get, or 3/4 of the voltage gated channels to get bigger or smaller signals?
Yes.
No, there's not a way to do that, right? So in fact, voltage gated channels kind of sound like an all or nothing type of situation, right? So where might we use an all or nothing type of channel? Action potentials, absolutely. All right. Now, what about chemically gated channels? Can I vary how many chemically gated channels I open? If I release one acetylcholine on a motor end plate, yeah, absolutely. Yeah, well, yeah, but so not so much even depending on the chemical, but how much of the chemical? If I release 3 acetylcholine on a motor end plate, how many of those chemically gated cation channels am I going to open?
3.
Yeah, not very many, exactly. If I dump a whole bucket's worth of acetylcholine on that motor end plate, how many are going to open then? Yeah, bucket's worth. So notice with that, we could vary how much is coming in and coming out. So we can't use voltage gated. We can use chemically gated. What about mechanically gated? Mechanically gated, remember, we're opening the channels based on how much we stretch the plasma membrane. Is stretching the plasma membrane an all or nothing, on or off type of situation? What do you think? Can you just, is there just one length you can stretch it to? So it's just, a neuron is either this big or that big, it's plasma
I
membrane.
think that's all or
No.
nothing.
No, it's not. We can put a little bit of pressure on it, a little bit more pressure, a lot of pressure on it. So notice the key with chemically gated and mechanically gated channels is we are able to vary how much we can open. And because we can vary how many we open, if we open a lot of sodium comes in and depolarizes the cell a lot. If we only open a little bit, then only a few sodiums come in and we get a smaller signal. So notice the advantage of chemically gated, mechanically gated channels is we can vary how many we open, and that allows us to have that variable signal that we want. We want to have, again, remember one of the keys to a graded potential is it's variable in amplitude. And chemically gated and mechanically gated channels allow us to do that. All right. Conversely, we could just open a few channels to get a negative signal. What would we call that signal when we go below the resting membrane potential?
Oh, repolarization.
Hyperpolarization. Oops. Be a hyperpolarization. And just out of curiosity, again, this hyperpolarization isn't going to last for very long. So eventually the cell is going to go back to rest. And when it goes back to rest, what do you think we call that process of going back to rest from being hyperpolarized?
Repolarization.
Yeah, repolarization, exactly. Repolarization means going back to rest. So it doesn't matter whether you're coming down or whether you're coming up, you're still repolarizing the cell. So if you depolarize, you have to repolarize and come back. If you hyperpolarize, you have to repolarize to come back. Now, again, we want to be able to vary the amplitude, making it smaller, making it bigger. So let's put all the pieces together. What are the types of channels that you would think we could use here to vary the amplitude and to hyperpolarize the cell?
Chemically gated.
Excellent. Chemically gated or?
Mechanical.
There you go. Channels. And what type of ions, plural, do you think that these would involve? Opening what type?
Sodium. Sodium.
Sodium's going to make it more negative. No, sodium wants to get to positive 66
Chlorine.
Excellent. Chloride is definitely going to be one of them. Excellent.
And then potassium channels to go out.
There you go. And potassium, absolutely. Because remember, potassium wants the cell to be negative 90. So you are correct. Potassium makes the cell more negative by leaving. When it goes out, when a positive ion exits the cell gets more negative. Which way is that chloride ion going to move?
Inside.
Yeah. So chloride will come in and that will make the cell more negative. And potassium will go out. And a positive ion leaving the cell makes the cell more negative. Right? Every time I give my kids $20, so if that positive leaves my pocket, I get more poor. All right. Excellent. So now we can know on our, that's the last thing I want to make sure, remember we emphasize, on the dendrites and the cell bodies, we produce these graded potentials. So if we think about our neuron, here is the cell body. No, let's make it black. Here's our cell body. Here are the dendrites. So in some location like out here, we are going to open up some voltage gated, some chemically gated or mechanically gated channels. We're going to produce a graded potential. Now, as we also know, these graded potentials, because they're small, tiny little waves, they only travel short distances. So if this neuron wants to provide this information to some target cell, is it going to be able to do that with a graded potential?
No.
No. So to travel long distances, what do we need?
An action potential.
An action potential, absolutely. To travel long distances, we need an action potential. So where do we make action potentials again?
Along the axon terminal.
Okay, well, so yeah, so perfect. So let's start there. Our goal is going to be to get to the axon, because our axon is where we're going to be able to produce our action potential. And someone remind me where I can produce my first action potential?
Trigger zone.
Trigger zone, excellent. So here in this region where the axon connects, what's this region where the axon connects again called?
Axon.
Hillock.
So at the trigger zone, in the axon hillock, we can produce an action potential. And that is the goal of these graded potentials. They can only travel short distances, but we only need them to travel a short distance. We need them to travel to the trigger zone. And if big enough, they can trigger, as the name indicates, an action potential. So they only travel short distances, but they only have to go short distances. That small positive wave just needs to spread down the dendrite, down the cell body to the axon hillock. And if we can get a big enough signal to that axon hillock, then we can produce an action potential, and that action potential can then travel the 3 feet down the axon that it needs to go. So that's our goal. On the cell body and dendrites, we get this information. We open our chemically gated, mechanically gated channels. That allows us to produce a variable amplitude signal, a graded potential. And our goal is to get that graded potential great. A big enough graded potential where we can reach threshold and fire our action potential. All right. Questions on that? All right. I've done an amazing job drawing this, but let's look at the pretty picture from your textbook. Again, here we see that depolarization and repolarization, that hyperpolarization and repolarization that we see there. And again, these only travel short distances, but we only need them to travel short distances because we just need to get to that axon hillock. All right. Questions on that? All right, then let's talk about the action potential. We've already got some introduction to the action potential, so we know a little bit about it already, but let's continue to add to what we know. Action potentials are large deviations from the resting membrane potential. They only occur on the axon because the axon has that special plasma membrane. And because vocabulary is always fun, what is the name of the special plasma membrane that allows the axon to produce an action potential?
Axolemma.
Axolemma. And now we can start talking about what makes the axolemma so special. What makes the axolemma so special is it has a special types, plural types, of channels on the plasma membrane that allow it to produce that big positive signal. And based on what we know so far, what types of channels do you think we find there? What types of gating do you think we're going to use?
Sodium.
Well,
Chemical and mechanical.
Electrical.
Well, so again, remember, one of the keys to an action potential is it is an all or nothing signal, right? Remember, it's either on or off. So what's going to happen, what it has a massive number of is a massive number of voltage gated sodium channels. And a massive number voltage gated potassium. Yep. Channels. So it is that massive number of voltage gated, both sodium and potassium channels, that allows our axon to produce an action potential. Again, with this set number and them being all or nothing, it has a set amplitude. In fact, as you can see here from the pretty picture, an action potential is about a positive 100 millivolt change. So no matter how big a stimulus you put into it, the action potential is going to be a 100 millivolt change. Big, huge positive signal, right? And like we talked about, it is all or nothing. I thought I said that's over here somewhere. Okay, it's all right. This big, huge wave allows it to travel long distances. But as I mentioned before, right, being a college professor, I have, of course, an Olympic-sized pool in my backyard because we can make that kind of scratch. And I have plenty of cars to spare as well. So if I grab one of my random cars and stand at the end of my pool and throw that car into the Olympic-sized pool, because of course I can lift cars over my head, I'm going to get a massive wave as a result of that. And that massive wave will travel a long distance. But with an Olympic-sized pool, is that wave going to be the same size when it reaches the far end of the pool?
No.
No. And if I stood at the edge of the Pacific Ocean and instead lifted an oil tanker over my head and threw it into the water, I would produce a massive, massive wave. But is that wave going to make it all the way to Japan? I know you're all imagining me holding a tanker over my head, and so that's why I'm not getting answers. No, of course not. It's not going to make it there. Absolutely not, right? And so while it can travel long distances, just being big isn't going to do it on its own. What's really special about the axon and what's really special about the action potential is it has an ability to what we call self-propagate. It makes itself bigger. What this means is I throw that car in the swimming pool and I produce a big wave, and that wave stays the same height the entire length of the pool. Or I throw that tanker into the Pacific Ocean and produce a massive wave. And that massive wave, not only does it make it all the way to Japan, but when it reaches Japan, it's the exact same size as when I first threw the tanker in to begin with. The beauty of this system then, is there a limit to how far I could send an action potential?
No.
No. If I had an axon that went from here to Seattle, Washington, I could use that axon to communicate with my grandmother in Seattle, Washington. I could send an electrical signal to her up there, and she would receive it. In fact, back in ancient times, that is what we used to do. In ancient times, there were these things called telephones. Right? Telephones were not the things in your pocket that you used to tweet and take pictures with and watch videos on and do everything but make a phone call. Phones were these things that were attached to walls by wires and had big, huge dials you had to spin. And what would happen is your wire was connected to a bunch of other wires that went all the way to Seattle, Washington. And so after dialing that thing 10 times, I would produce an electrical signal, and that electrical signal would spread across that wire all the way up to Seattle, Washington, and I could have a communication on the phone with my grandma with that electrical signal. Well, I could do the exact same thing with an axon. That axon signal can travel as far as you need it to go because it has this ability to self-propagate, to self-strengthen, to maintain that 100 millivolt amplitude. All right, so let's see how to do this. Now, the last thing we need to understand, and I think this picture will help us with this. Let's start here. Perfect. Here we see examples of our voltage-gated sodium and voltage-gated potassium channels. Obviously, both are gated by voltages, and it, of course, opens at threshold. And what is threshold again? Negative 60 millivolts. Excellent. Perfect. And that is true for both our voltage-gated sodium and our voltage-gated calcium channels. Potassium. 50 millivolts. Excellent. And in fact, if we look at the pretty picture here, on the pretty picture, we can see those activation gates, those big positively charged proteins that we know are going to swing open when we reach threshold. So that is something that is true for both the voltage-gated sodium and the voltage-gated potassium channels. However, there are two big key differences between the two of them. Our voltage-gated sodium channels both open and close very quickly. Whereas our voltage-gated potassium channels both open and close very slowly. The other big difference is this fellow right here. Notice there are two additional proteins on our voltage-gated sodium channel. Remember, as we talked about, these two proteins have very technical terms, the ball and chain. So our voltage-gated sodium channels have the ball and chain inactivation gate. And since it has the inactivation gate, of course, that means that our voltage-gated sodium channels can inactivate. That ball can wedge itself in there. So if you think about it, our voltage-gated sodium channels have three states. They can be closed, they can be open, and they can be inactive. And someone remind me again about what the deal is when it's inactive. When it's inactive, the sodium's not going to be able to pass through the channel, even though the channel is open. But how do we get it to not be inactive anymore?
Close it first.
Yeah, exactly. Remember, once it's inactive, it must close before it can be opened again. All right. Excellent. So when it's in that inactive state, it must close to be able to open again. Obviously, if you notice from the picture, our voltage-gated potassium channel has no ball and chain. So there's no inactivation gate. So of course, that means it only has two states. It can be closed and it can be open. All right. Questions on that? All righty then. Our table is set. Let's go through an action potential. And as always, let's go through it twice. I want to draw it first and talk about it first. So let's go now that we understand all the pieces. So again, questions on any of this? If you don't understand this, it's just about to get a whole lot worse. So questions on this before we get started. All right, let's discuss an action potential then. We can keep the graph, although we're going to have to erase some stuff. I don't want to keep this picture, but I don't think I'm going to have room for it. Let's try. All right, we'll see if we can sneak this in. Now here, this might help. Let's do this. If I do that. There we go. That may let me keep my picture. Excellent. So again, notice what we are doing here is we are focusing right here. All these events that we are going to be talking about for our action potential. And again, let's at least put the label up here. This action potential occurs, or let's say it this way, starts at the trigger zone. So what we are talking about right here is the first beginning of our action potential, or the initiation of an action potential. Now, as we know, this cell is at its resting membrane potential, where it is happily staying, at negative 70 millivolts. And if left alone, how long will it stay at negative 70 millivolts for?
Forever.
Forever, absolutely. It will happily stay there forever if you don't mess with it. However, we want it to do work. So what we are going to do is we have to stimulate it in some way. We have to disturb it. And how are we going to disturb it? What is the first step? The first thing we're going to need to do in this process to change this cell and get some effect, some kind of change to occur?
Huge positive impulse.
Well,
stimulus.
We want a huge positive stimulus. We want that action potential. But to produce an action potential, as we know, we need to open voltage-gated channels. And how do we open voltage-gated channels?
Depolarization.
To
reach
what?
Threshold.
Excellent. So we need some type of disturbance. And we need to get it to reach threshold. So what kind of a disturbance, what kind of change in the membrane potential could I use to cause a disturbance to get it to reach threshold at the axon hillock?
A positive.
A positive what?
Greater potential.
Graded potential. There you go. Exactly. So in this case, what we need is we need a positive graded potential. And that positive graded potential travels from the dendrite or the cell body to reach the trigger zone. And as a result of that, we see a depolarization. And so let's say, for instance, it causes a 5 millivolt change. What happens then?
Nothing.
Exactly. It's going to go back down and nothing's going to happen. What if it produces an 8.5 millivolt change or a 9.9 millivolt change? What's going to happen then?
Nothing.
Nothing, absolutely. We need a big positive signal, but we need this big positive signal to be big enough to reach threshold, right? That's going to be the key. We need a depolarization that is going to be big enough to reach threshold. There you go. There we reach threshold. So if the depolarization reaches threshold, then that's when the magic is going to happen. And in particular, what is that magical thing that's going to happen if we reach threshold?
Voltage gated channels opens.
Which ones?
Sodium.
All of them.
All of them. If we reach threshold, all voltage gated channels will open. All right. But you are correct. When all voltage gated channels open, do they all open at the same time?
No.
No, which one's open first?
Sodium.
Exactly. So when we reach threshold, the immediate thing that's going to happen is all the massive number of our voltage gated, and I've written voltage gated enough times now where I can abbreviate it, VGNA, for all of our voltage gated sodium channels are going to open. And we are going to get a massive influx of sodium. Why is so much sodium coming in?
To make it positive.
Why? You were correct. It makes it positive, but why does all this sodium enter the cell?
To reach its equilibrium.
Right. Because it is trying to reach its equilibrium potential. So we're going to get a massive, massive influx, massive, rapid influx of sodium as it goes rushing up, trying to reach its equilibrium potential. Notice this produces a big positive signal. And what's another name for a big positive signal?
Threshold.
Nope.
Depolarization.
True, depolarization, but in this case, we have a very big, rapid, positive signal.
Action potential.
Action potential. Positive signal, guess what? Our goal was to make an action potential, and guess what? We just produced our action potential. End of the story.
It's done.
Okay. Yeah, it's done. Well, not really. But here's what's happened. We have produced our action potential. But as we know from the muscular system, if I want to move my body through space, do I have one neuron produce one action potential and then it gets to take the rest of the day off? No, we need lots of action potentials to be able to just even lift up our cup of coffee in the morning. So while here we've gotten our big positive signal, not only do we have to get a big positive signal, but we then have to get this cell ready to produce a second big positive signal. So yes, we've gotten our action potential because sodium is trying to reach its equilibrium potential, but this is really just the beginning of the story. We need to get back to rest so we can do it again. Now, our goal, well, not our goal, but sodium's goal is to reach its equilibrium potential. So sodium tries to reach its equilibrium potential. That's why it's moving. And again, I think the way I phrase this question will probably give the answer away. Do you think it reaches it? Does it make it there? No, does not get there. Instead, it peaks at positive 30 millivolts. So we have now a fifth number we need to know. Our peak of the action potential is positive 30 millivolts. Of course, if we do some quick math, what membrane potential did we start at? What's the resting membrane potential?
Minus 70.
Minus 70. Excellent. If the peak of our action potential is positive 30 millivolts, what's the total change?
40.
Going from negative 70 to positive 30 is how big of a change?
40.
100.
Minus 40.
100
millivolts.
millivolt change. It's a positive 100 millivolt change. Remember, so again, going from negative 70 to 0 would be 70. 30 more would be 30 on top of that. It would be 100. So it's a 100 millivolt change, total change. Big, huge peak, big, huge positive signal. Now, there's two reasons it doesn't reach the equilibrium potential of sodium. It's trying to reach there, but it does not get there, and there are two reasons. The two reasons it doesn't get there, and let's go back to blue.
Inactivation gate.
Exactly, that's definitely one of them. The first reason is that our voltage-gated sodium channels inactivate. So that ball of chain wedges itself into the channel. And once it's inactive, that means no new sodium can enter the cell. Because once that ball of the ball and chain wedges itself in there, it's, even though the channel's open, sodium cannot flow. So no new sodium come in, and if no new sodium's coming in, it can't continue to get positive. But the second thing that happens has to do back with that threshold. Remember, threshold is when all voltage-gated channels opened. And now, finally, those slow voltage-gated potassium channels have finally opened. And when voltage-gated potassium channels open, which way does potassium want to flow?
Out of the cell.
Excellent. So again, remember we have a massive number of these, and so we get a massive efflux of, the massive efflux of potassium out of the cell. And when a positive ion leaves the cell, what does it do to the cell?
Repolarize.
Well, you're absolutely correct, but it makes the cell more negative.
Yes.
And in this case, you are correct. It is going to, so potassium leaving is going to repolarize the cell. And so it's not getting positive anymore. No more sodium is, no more sodium is coming in. And potassium is leaving. So as potassium is leaving, it is repolarized in the cell. Now, two interesting things happen on the way down. The first interesting thing that happens on the way down is the cell passes threshold on the way down. As the cell passes threshold on the way down, so I guess this was for, I guess I'll continue to number this. This is 3, so this would be 4. So what happens is as the cell repolarizes, it passes threshold. And what happens when the cell passes threshold on the way back down?
Voltage gates close.
Exactly. What types?
All of them.
All of them. However, do all of them close at the same time?
Sodium first and the potassium.
Excellent. So as we pass threshold on the way down, our voltage-gated sodium channels close immediately. However, you are right, our voltage-gated potassium channels close with a delay. So they're much more slow. They're going to close with a delay, so they don't close right away. Now, a second interesting thing happens on the way down. On the way down, oops. Blue. And I want there. On the way down, the cell is going to hit resting membrane potential. The cell is now happy. But what's driving the change here? What's making the cell more negative?
The leaving of potassium.
Potassium is leaving. Now, is potassium going to be happy at the resting membrane potential?
No.
No. Where does potassium want to be?
N.
It wants to be at its equilibrium potential. Absolutely. So what happens here is potassium is leaving because potassium wants to reach its equilibrium potential. And so what that means is not only does potassium repolarize the cell, but potassium also makes the cell go past the resting membrane potential. So let's draw another quick line here to emphasize that. This is our, here is our resting membrane potential there. So potassium isn't going to be happy at the resting membrane potential. So not only does potassium doesn't just repolarize, but it also makes the cell go below its resting membrane potential. And what do we call that again?
Hyperpolarization.
Yeah, it hyperpolarizes the neuron. This hyperpolarization we call the undershoot, because it doesn't care about the resting membrane potential. It's trying to get to its equilibrium potential. Now, do you think it gets there?
No.
No.
Nope. Does not reach the equilibrium potential of potassium because finally, with a delay, the potassium channels close. So no new potassium into the cell. So eventually, it stops off. Now, does this cell stay hyperpolarized forever?
No.
No, we need the cell to repolarize. So eventually the cell repolarizes. And how do you think it does that? How do you think it gets back to its resting membrane potential?
Close potassium, inactivate potassium.
Well, again, remember, we have the channels closed now. These voltage-gated channels are closed. Leak channels, definitely using leak channels will allow things to try to get back to where they want to go. But remember, sodium's inside because it wants to be inside. Potassium's outside because it wants to be outside. We want that sodium back outside. We want potassium back inside. We want to put these ions where they don't want to go. And to do that, we need to use ATP. So using leak channels and pumps, right? Using ATP, we will, like the sodium potassium ATPase, we reestablish the resting membrane potential. And at that point, our cell is back at rest and our action potential is done. So again, I'm putting numbers here. You don't have to number them. You don't have to use these numbers for the stages of it. But I think if nothing else, for the picture here, it'll help us to make some sense of everything that is happening. And that is our action potential. All right. Questions on that? All right. This is a lot of information. So here's what we're going to do. Let's go ahead and take our first break right here. When we come back, we will go through this entire process again with all the pretty pictures from your textbook. Your textbook does a really, really nice job of describing this process and has some great pictures to go along with it. So we'll take a look at that and talk about that and then move forward from there. All right. Any questions? All right, it is 9:10, so let's take a 15-minute break. That means we'll come back at 9:25, and at 9:25, we will pick up from there. Start the recording. Oh, am I recording? Oh, good. Okay, yes. Start recording from there. All right, see you guys in 15 minutes. All righty. Any questions? All right, then let's go through the whole process again, but using the pretty pictures from your textbook. Again, here we see our starting point. Our starting point is when the neuron is at rest. And again, we're measuring the membrane potential at our axon hillock. And our starting point is negative 70 millivolts. And in both our sodium and our potassium channels at this state are both in their closed state. We are below threshold and it is closed. Oops, where's my, there it is. Excellent. The first thing we need then is to reach threshold. We need some type of disturbance. And that disturbance comes from opening, right? We need to open either chemically gated and or mechanically gated. Sodium channels, most likely, but also calcium could play a role in this as well. Although, like I said, with calcium, things make wonky things occur. And we get a small depolarization. We get a graded potential. And that graded potential needs to spread to the axon hillock. And the key with that graded potential is it has to be big enough to reach threshold. So as long as it's at least a 10 millivolt change, then we are going to reach threshold and the magic's going to happen. But remember, threshold is just the point that we open the channels and all the channels open. So if instead my graded potential is a 20 millivolt change, do I open twice as many voltage gated channels and do I get an action potential that is twice as big? No. Remember, this is an all or nothing and it has a set amplitude. So it doesn't matter how high above the threshold you go, the key is just to reach threshold. It's all or nothing. If you reach threshold, the magic happens. If you don't reach threshold, nothing happens. Now, threshold is the point where all of our voltage gated channels open, but do both of our voltage gated channels open at the same time? Hello? These are the easy questions, folks.
They
Do all
all
of our
open at the same time, but the potassium opens slower.
Excellent. So the very first thing that happens, the very first event that'll occur upon reaching threshold is that our voltage gated sodium channels open. And of course, which way does sodium move? Into the cell or out of the cell? Again, these should be the easy questions. In. Why? Why does sodium enter the cell? Right, it's trying to reach its equilibrium potential, which is what's the equilibrium potential?
66.
Yeah, positive 66 millivolts, absolutely. So sodium rushes in, trying to reach its equilibrium potential of positive 66 millivolts. And we get our rapid, big, positive signal. This right here, sodium entering into our voltage-gated sodium channels, give us that big, rapid, positive signal that we call the action potential. This is the action potential. So if you think about it, really the production of the action potential is really just the first step. Then it's all about getting back to rest so we can do it again. So we get this big positive signal. The cell rapidly repolarizes, trying to reach the equilibrium potential of sodium, and we get our big positive signal. Now, sodium is trying to reach its equilibrium potential, but does it actually get there?
No.
No. Because how many things occur?
Two.
Two, exactly. Two things occur. Two things occur. What's the first thing that occurs? And again, these are occurring at the same time. So again, you can do them in any order. But what are the two things that occur?
The voltage gated channels are inactive, so no new sodium can go inside.
True. Absolutely true. Although the one thing you want to be doing is you want to be careful. Remember, not all of them inactivate, just the sodium. So it's the voltage gated sodium channels that are inactivate. But you're absolutely correct. As we see here from the pretty picture, that ball of the ball and chain wedges itself into the channel. So even though the channel is open, sodium cannot flow through because it is inactive. So our voltage gated sodium channels inactivate. And what's the second thing that stops it from reaching its equilibrium potential of sodium?
Potassium flowing out.
Exactly, right? So again, no new sodium can come in. It can't keep getting positive, but it could stay depolarized, but it doesn't. The reason it doesn't stay depolarized is those voltage-gated potassium channels finally open. And when they open, which way does potassium move?
Out.
Out of the cell, absolutely. And a positive ion exiting the cell makes the cell more negative. So no more sodium coming in, no more positive signal, lots of potassium leaving the cell makes the cell more negative. So the overall effect is we start to go back towards the equilibrium potential. We start to go back towards the resting memory potential. And what do we call that process of going back towards the resting membrane potential?
Repolarization.
Repolarize. However, we know the trick now. Yes, potassium is repolarized in the cell, but not because it wants to be at the resting membrane potential, it wants to be at its equilibrium potential. So not only is it going to repolarize the cell, but what else is it going to do? Yeah, it's going to hyperpolarize it. Because it is trying to reach, so it repolarizes the cell and also hyperpolarizes the cell as well. Excellent. So again, potassium rapidly exits the cell. On its way down, and again, we can draw a line here to emphasize this, on the way down, we pass threshold. When we pass threshold, something special happens. And what's that special thing that happens as we pass threshold?
Gates close.
Yeah, the gates close, right? Now, sodium, of course, closes right away. So again, notice those doors swing down. And the significance of that sodium channel closing right away is that it pops the ball out. And so now, once we pass threshold, on the way down, the voltage-gated sodium channels are no longer inactive. Now they're just closed. And the nice thing about being closed is they can be opened again. Can't be opened if it's inactive. It has to close first. I know it seems silly that I keep making a point of emphasizing this, but we'll see why we're doing that in just a minute. Now, these close right away. Do our potassium channels close right away? No, and so they don't close right away. Then that means the cell is going to continue to try to reach the equilibrium potential of potassium, meaning it's going to go right past the resting membrane potential and actually hyperpolarize the cell. And again, we call that hyperpolarization the undershoot. Now, potassium's trying to reach its equilibrium potential, but does it get there? No, because again, it passed threshold on the way down. It's slow, but eventually that potassium channel does indeed close. And when it closes, it stops hyperpolarizing. course, it's still hyperpolarized, so we need to get the cell back up to its resting membrane potential. And how are we going to do that?
Using pumps?
Yeah, exactly. Using pumps and leak channels too, but really most of the time it's getting ions to go where they don't want to go. And to get those ions to go where we don't want them to go, we need to use ATP. So we're going to use active pumps to get the ions back where we want them to be. And that is going to reestablish our resting membrane potential. And so at the end of this process, we have a graph that looks a little something like this. Now, normally on this exam, I could almost guarantee you would be drawing this action potential. All right, you are not going to be, I'm not going to require drawings on this exam because again, we only have that whiteboard to be able to do that on the computer that we'll be able to. So the good news is you don't have to worry about doing any drawings. The bad news is that means you're going to need to make sure you definitely describe this with your words. If you want to use the whiteboard to draw this to complement your answer, you are welcome and encouraged to do that. The one thing I do strongly encourage you to do is once you've completed your drawing, leave it on the screen for about a minute just to make sure that I can fully capture and see the image clearly. But again, it's not going to be required. But if you want to draw to supplement your answer, you are welcome to do that. But make sure you are descriptive. You're going to get graded for the words that you are writing and for your explanation of this. All right. So notice when I did it in 4 steps. Here, the simple picture from your textbook just shows the 3 main processes that are involved. And then the reestablishment of 1. But again, I don't care how many steps you use as long as you explain all the information. All right. So that is our action potential, period, end of story. Questions on that? Again, if this doesn't make sense, now's the time to ask because it's only going to get worse from here. All right, so here's my question for you. As we learned in our muscle system, do we typically do anything with our body by just sending one action potential to tell that muscle to lift that cup of coffee up to our face?
No, it's multiple.
No, so we need to not just produce one action potential on a neuron, but really we have to produce many action potentials. So this is great. We've produced one action potential, but if you think about it, our goal is really going to be to produce many action potentials. And do you think there's going to be a limit on how rapidly we can produce them?
Yes.
Absolutely. There's going to be a limit on how quickly we can do this. So let's think about this. What actually produced the action potential? If I want an action potential, what is the number one thing that I have to do? What is the ultimate thing that I have to do to get an action potential? Excellent. I need sodium to enter the cell through what?
Channels?
What kind of channels?
Voltage gated?
Bingo. So what the action potential actually is a massive influx of sodium through voltage-gated sodium channels. So if you think about it, to produce an action potential, You have to open voltage gated sodium channels. Right? Here I am sitting in my office with my doors closed because I talk loud and my kids get annoyed by hearing me, especially when they're on break. So I have to have my door closed. So if I want to leave this room, I have to open the door. If I want an action potential, I have to open the voltage gated sodium channel. Where on this chart does that opening of the voltage gated sodium channel occur?
Depolarization, 2.
To what?
Number 2.
Okay, well, but no, be more precise. What do I actually have to do to get the voltage gated sodium channels to open?
Reach threshold,
And what's the threshold again?
-60.
Negative 60 millivolts. I'm cheating because your book's got negative 55 there, but negative 60 is a more accurate number. And more importantly, it's the number I use, so that's the one you're responsible for. Exactly. To open the door, I need to reach threshold. And once I reach threshold, if you think about it, at this point right here, when I pass threshold, I have opened my voltage gated sodium channels. So opening the voltage gated sodium channels gives me an action potential. If the voltage gated sodium channels are open, can I open them a second time? If I open this door to get out of my office, can I open it a second time once it's already open? Yeah, after they close, I can, but not before then, can I? So notice, if you think about it, no matter what I do to this cell while these channels are open, I cannot open them a second time. Right? Again, it's physics. Once the door is open, I can't open it again. Not a lightning bolt, right? Not a message from God. Nothing is going to get these doors to open a second time if they're already open. Meaning I can't produce an action potential. Wasn't there a phrase or term we used for a cell when no matter what we did to it, it couldn't produce a second action potential? Refractory period. And in this case, there is absolutely nothing we can do to produce a second action potential. So this is the absolute refractory period. Now, what about when this is coming down? What's the state of my sodium channel as the cell is repolarizing? My voltage gated sodium channels are in what state?
Inactive.
And if they're inactive, is there absolutely positively anything I can do to open them again?
Close them.
You have to close them.
I have to close them first. So when they're inactive, there's nothing I can do to open them. So could I get a second action potential right here, or 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 all the way to that point right there? So notice from this period of time when I first opened the channel to this period of time when I pass threshold on the way back down, this period of time is that period of time where there is absolutely positively nothing I can do to get this cell to fire a second action potential. And so this is my absolute refractory period. Now, you guys have hit it on the head. Once I pass this point right here, my voltage gated sodium channels are closed. And if my voltage gated sodium channels are closed, now can they be opened again?
Yes.
Yeah, they can be opened again. At this point, we can produce a second action potential. But we do have a problem. What was the change that I had to do at the beginning to reach threshold? How big of a change did I need at the very beginning to reach threshold?
10.
Yeah, it was a positive 10 millivolt change, right? That was what we needed at that point to reach threshold. But notice this cell is repolarizing. This cell is getting more negative. If I happen to be at this point on my graph and I do a 10 millivolt change, is it going to reach threshold? Is that going to get me to threshold?
No.
No. So notice technically at this period of time, my channel is closed and it can be open. But notice what's going to happen. I'm going to technically I can open the voltage gated sodium channels during this period of time, but it is going to take a larger stimulus to reach threshold. So it's not impossible to reach threshold, it's just harder. It takes a bigger stimulus to do that. And so what we call this period of time is the relative refractory period. It's the relative refractory period because I can produce an action potential, right? Everything from here forward, I can produce an action potential, but it takes a bigger stimulus. And when do you think the relative refractory period will end? When will the same stimulus that gave us an action potential the first time give us an action potential the second time?
When it reaches threshold?
Well, not when it reaches resting membrane potential, exactly. Once it's no longer hyperpolarized, once it reaches resting membrane potential, the refractory periods are over. And now the same stimulus that gave us an action potential the first time will give us an action potential the second time. Now notice the timing of these. Look, the absolute refractory period is less than 2 milliseconds. The relative refractory period is less than 5 milliseconds. So we're talking about very, very brief periods of time. But there is a very tiny period of time where first it is impossible to produce an action potential, then it's harder to produce an action potential. And we call those the absolute refractory period and the relative refractory period. Questions on that?
So the relative refractory period is the time from the point that it reaches threshold to hyperpolarization and back up to the resting potential?
I'm sorry, say that again.
The relative refractory period is from the time that it coming back down, it hits threshold, back down to hyperpolarization, and then back up to resting membrane potential?
Correct, absolutely. Because again, once we pass threshold on the way down, that is when we're going to be able to open those voltage gated sodium channels again. So it will be possible to get a second action potential, but all that potassium is leaving. And so that's going to make it harder, right? It's making it more negative. So typically the same stimulus won't get us there a second time until we get back to rest. Once we're back at rest, then that same stimulus that got us to threshold the first time will get us to threshold a second time. It's possible to reach threshold. It's just going to take a bigger stimulus, a bigger signal to get us to threshold during this period of time. So yes, from threshold back to the resting membrane potential. That is correct. Excellent question. Any others? All right, I need to erase this. More fun with graphs. I love this graph from your textbook because I think this does a really, really nice job of showing us what is happening. Obviously, here we have our we'll go ahead and use purple. Stick with it. Shows us our action potential, right? We depolarize the threshold, rapid depolarization, rapid repolarization, hyperpolarization, and back up to rest. But what it also does a really nice job of showing us is why this occurs. Notice here, it shows us the permeability of sodium. Notice when we reach threshold, at that point of threshold, all the voltage-gated sodium channels open really, really quickly. So we have a massive increase in the permeability of sodium. Conversely, notice when we reach threshold, our voltage-gated potassium channels are much slower to open. It takes a much longer time for us to get that potassium to leave the cell. Now, while those sodium channels all open immediately, they then almost just as quickly inactivate. And when they inactivate, no more sodium can come in. And so once again, the permeability of sodium drops basically to zero just as quickly as it went up. And notice potassium. By the time all the potassium channels have fully opened, that's practically the time we're reaching threshold on the way back. And so again, with a delay, they are slowly going to close until, again, none is there as well. So what's nice about this is this also does a really great job of showing us how the sodium channels open quickly and then inactivate quickly. Our potassium channels open much more slowly and close much more slowly. And so we see this with this really nice graph here. And then lastly, as we've talked about, this refractory periods, just like we saw with the twitch, the refractory period has nothing to do with this action potential. Refractory periods are all about when can we produce our next action potential. So again, when we talk about refractory periods have nothing to do with this action potential and everything to do with when we can produce our next. Refractory periods determine when we can produce a second action potential. Have nothing to do with this action potential and everything to do with when we can produce a next. And during that absolute refractory period, is there absolutely anything we can do to produce a second action potential? No, because first the doors are open, and if the door is already open, we can't open it a second time. And then the channels are inactive, and if they're inactive, they can't be opened. However, once we open those channels, then we reach our relative refractory period. At this point, now our channel is closed, and again, that's the key. At this point right here, our voltage-gated sodium channels close. So once closed, they could be opened again, but the cell is hyperpolarizing. So while it is hyperpolarizing, until it gets back to rest, during this relative refractory period, we can produce a second action potential. It just takes a stronger stimulus to get it there. And then once it's back at rest, the refractory period is over. All right. Questions on that? All right, excellent. Congratulations. There you go. Everything you ever wanted to know and more about the action potential. Now we've produced it. Of course, now that we've produced our potentials, both graded and action potential, we still have to propagate that action potential down the axon, and we'll see that there are two ways to do that. And then we still have to communicate with our target cell. So we still have some work to do on this action potential, but this is the material that I wanted to cover for today. Where is it? Hold on a second. No, we do need to propagate it. All right, so we still have some work to do. Yeah, we're doing this first. Okay, excellent. All right. Questions on this? So as I mentioned, everything that we have done so far, we have been focused on this region right here, that target zone. We have produced our graded potential on the dendrite, on the cell body, and moved it to the axon hillock. And then here at the axon hillock, we have produced that first big positive signal, that action potential. So now our goal is going to be to propagate it. And we are going to propagate it two ways. First, without myelin, and then with myelin. Now, again, myelin was that insulation we're going to use to insulate, but also speed up the action potential. And what are the two cells that we said, the two neuroglial cells?
Schwann.
And oligodendrites.
Excellent. Schwann cells and oligodendrocytes. Where do the Schwann cells produce our myelin sheath?
Peripheral nervous system.
There you go, peripheral nervous system. And where do the oligodendrocytes produce our myelin sheath?
Central nervous system.
There you go. Excellent. So we will propagate it with myelin and without myelin and see how those two processes are both similar and different. All right. Like I said, I can pretty much guarantee you that 3 of these essay questions are going to, of these 3 essay questions, one of them is likely to be on the exam. You need to either produce an action potential, propagate it without myelin, and propagate it with myelin. At least one, and possibly more than one of these could be on your exam. All right. Questions on that?
So the propagation is done, sir?
No, I'm going to explain that next. That is what we're doing next.
Okay, I thought it's done.
Nope. Like I said, all we've done so far is just produce that action potential right here at the axon hillock.
Thank you.
Everything we did, and let's go back. All of this that we've seen right here is just happening at that axon hillock. So what we need to do now is propagate it. So let's do that. Let's do it first on the unmyelinated axon. So let's grab the whiteboard for this. Remind ourselves what we are doing. So let's see, for this, I'm going to need you down there. And let's grab this and put it there. And then this needs to be up here, so it's out of my way. This needs to be up here, so it's out of my way. All right. Oh, and somewhere I've lost my chat. There it is. Oh, Laura, I just saw your question. Did I cover the relative refractory period for you okay, or do we need to go over that again?
I think it's okay.
Well, no, I don't mind going over it again. Like I said, I think this is just going to get worse as we continue on. So let's talk about it. The important thing to remember is that to produce an action potential, we need to open our voltage-gated sodium channels. All right? We know that we have a big, massive number of sodium channels, and we need to open them all at the same time to get that big positive signal. Okay? Now, to open them, actually, let's go ahead and leave it big. To open the voltage-gated sodium channels, we must reach threshold. So we have to get a big enough stimulus to get the axon hillock to reach threshold. When the cell is at rest, that's easy. We basically need to get from -70 millivolts to -60 millivolts, and there's nothing else going on in the cell. The cell is at equilibrium. And we need to get from -70 millivolts to -60 millivolts. So obviously that means we need a positive 10 millivolt stimulus, right? And of course, we're going to get that stimulus from a graded potential. We comfortable with that part? That part makes sense? All right, so here is our problem. During the relative refractory period, the cell is not at equilibrium. We have massive amounts of potassium leaving the cell, and that is making the cell more negative. All right, so we've passed threshold. So the good news is we've passed threshold. So our voltage-gated sodium channels are closed and can be opened. All right, that's the good news. So let's put that back up at the top. Cut that. So the good news is our past thresholds, our voltage-gated channels are closed, and so they can be opened again. The problem is this occurred during the relative refractory period, while that massive amount of potassium is leaving the cell, making the cell more negative. All right, so again, think of it this way. You've got a cup of water, and that cup of water is at 90 degrees Celsius, and you want to get it to boil. To do that, you just need to add 10 more degrees to it, and suddenly it's going to boil. All right? And so you add that 10 degrees of heat to it, and that's enough to get it to boil. Well, what's happening here is that someone's pouring cold water to it at the same time. Right? Because potassium's leaving the cell and making the cell more negative, if someone's pouring cold water into my cup, is me just adding 10 degrees going to be able to bring it up to boiling? No, I can get it to boil, but I'm going to need to add more heat. It's going to take a bigger signal. And that's the key here. It is possible to reach threshold, but we need a bigger signal than the original one. And so because that potassium is making it negative, we need a bigger signal to get that water to boil. We need more energy to get it to boil. We need a bigger signal to reach threshold. And if we can get that big signal, then we'll get a second action potential. But if not, it won't until it gets back at rest. Once we're back at rest, once we're back at equilibrium, right, at the resting membrane potential, then that same signal as the first time will reach threshold, and it's no longer being suppressed. Does that help it to make more sense?
Yeah, I initially was just not understanding when it started and when it ended, but
okay. So so the relative refractory period starts at threshold, on threshold on the way down. So at threshold on the way down, as it's repolarizing. That is when we close the voltage-gated sodium channels and kick the inactivation gate out. At that point, that sodium channel can now be opened again. So that is the beginning of the relative refractory period. And it ends once the cell is back at resting membrane potential. At that point, there's no more any suppression. And so that is when the relative refractory period would end. Okay. Excellent. No, I'm glad you asked that because I'm sure other people are confused by this as well. I know way too many people are quiet, so I appreciate the people who are willing to speak up. Again, remember, I'm a firm believer of the only bad question is the question not asked. If you're confused about something, I guarantee you somebody else in the class is as well. And especially with so few of you here, you got to be bolder about speaking up to make sure you're getting this information so that you can be successful on the exam. All right. Excellent, excellent, excellent. Thank you for asking that. All right. We still have 22 people enrolled in this class. Now, 19 took the exam and 14 are here today. So again, but when technically we still have 22 people enrolled in this class. So again, sometimes when we return the exams and there's fewer people, I know there is some attrition. And I'm sure there's some attrition that happened from this one as well, especially for those people who didn't take it. I think today, this week is a little bit special because like I said, we're in this unique situation where we're doing this online and we're stuck doing this at home. And for many people, especially people who have kids, they're off this whole week. Most of these kids. So again, one of my kids is back at school 5 days a week. One of my kids is back at school 2 days a week. And they're off. But again, I have teenagers. So quite frankly, I don't even know if either of them are even awake yet. But the people with little kids, it's much, much more challenging. So I'm trying to be understanding. That's why I made a point of pointing out that there's going to be a daily quiz on Wednesday. You don't get extra participation for being here. Again, you are, you're paying to be here so that you're getting your money's worth by being here and getting the advantage of learning this material and helping you to be successful. But remember, there are participation points, and people who aren't actively showing up on a regular basis will be losing participation points for that. Yes. So you're not getting extra credit that way. And again, remember, participation points are not extra credit. It is a grade. So by being here, you're maintaining that participation grade, whereas those people are not, are likely losing participation points. All right. And again, you don't lose. It's not like we'll miss one class, miss 3 participation points. I understand life happens and things happen. If you are chronically missing this class or chronically not coming to class actively, then that's when you start losing participation points. All right. Okay. Anything else on the initiation, production of an action potential before we start focusing on propagating? All right, so let's propagate an action potential. And again, we will do it first without myelin. Now, we need to remember what we're doing. As I talked about up to this point in time, we have been solely talking about what's happening at that axon hillock. We have the dendrites. And again, up to this period of time, we have focused solely on what's going on right here at the axon hillock. So let's draw that axon hillock. Here's where we've been looking at it big. I mean, a little. Let's look at it big. So here,
sorry, sir.
Yes.
Sorry, I would like to jump in and just ask the question that a few minutes ago we explained the process on unmyelinated axon. This was only the action potential, not the propagation, right?
Yes, what we described was the production of an action potential. Okay. And that production of an action potential has nothing to do with whether it's myelinated or not, because the myelination is located along the axis along the axon. We haven't talked about the axon other than the axon hillock. Everything we've described up to this period of time all happened right here at the axon hillock. So we produced an action potential, but we have not, we've produced an action potential, but we have not propagated it yet. What we're doing now is propagating it. Okay?
Thank you.
Yep. All righty. So here is our axon. Here is our cell body, the beginning of the cell body. Our axon hillock is located here. And we know that what makes our axon so special, allows it to produce its action potentials, is that it has a massive number. So where should I write this? Let's write this here. Massive number of voltage gated sodium and voltage gated potassium channels. And we can just draw those as little hash marks. Ugh. This is going to be forever. Let's do it this way. Do, 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 do. Along the entire length of our axon, we have all these voltage gated sodium and voltage gated potassium channels. Now, again, we know both of these channels are present on the axon. And we know that in the axon hillock starts with none, and then it ends up with a point where there's a massive amount. And we know that there's that trigger zone. So let's cheat and make, oops, no, let's make it pink like the one we drew before. Let's say this is the trigger zone right here. Again, it's not, trigger zone isn't something we can see, but we know this is the area where there's finally enough of those voltage gated channels to affect the change that we want. Now, our goal is to propagate the action potential. And while we have massive numbers of both voltage gated sodium and voltage gated, oops, somehow I lost my potassium. Yeah, let's do it this way. While I have massive amounts of voltage gated sodium and voltage gated potassium channels, if you actually think about it, which ones are actually responsible for the action potential?
Sodium.
Right.
Sodium.
So it is the voltage gated sodium channels that produce the action potential. So those are really the ones that we are going to be focusing on. We know all the other events have to occur if we're propagating the action potential. But for right now, we're just going to, on producing the action potential. But right now, we're just going to focus on the propagating. All right. So let's think about what happens. We know the process starts with our stimulus. A graded potential travels down the axons, down the dendrites and the cell body to the axon hillock. And as it travels down the cell body and the dendrites to the axon hillock, it is a big enough depolarization to reach threshold. And if it is a big enough depolarization to reach threshold, what happens here at my axon hillock? What occurs here at the axon hillock?
Voltage gated
All the sodium channels open.
There you go.
Oh.
Our voltage gated sodium channels open. We have a massive number voltage gated sodium channels open. And of course, when those voltage gated when those voltage gated sodium channels open, what happens?
You produce the action potential.
Right, why? You
A
open
massive number of the sodium goes into the cell and to maintain its equilibrium.
Absolutely. So, well, again, it's not reaching, it's trying to reach its equilibrium potential. Absolutely. So what ends up happening is these voltage gated sodium channels open, and we have a massive influx of sodium at this point right here. So we get a massive amount of sodium that enters the cell right here. And of course, that produces our action potential. We get that big positive signal. And how big is it again?
Minus 60 millivolts.
100 millivolts.
Yeah, our action potential is a massive 100 millivolt change. We get that big, huge positive signal, that big, huge, massive 100 millivolt change. Excellent. Perfect. No new information here. We've changed our perspective a little bit of how we're looking at it, but nothing new so far. Everything we've talked about so far is what we've already talked about, no new information. However, what we haven't talked about is what happens with that sodium. If we have a massive amount of sodium that we pour into this axon right at this location, is it going to stay right in this location? If you're making a pitcher of Kool-Aid and you pour the crystals into one space, do they stay just there in that one space? No. So what's going to happen is we are going to get diffusion of sodium ions. Some of these sodium ions are going to spread backwards into the cell, into the cell's body, into the dendrites. And if that happens, is that going to affect any kind of change in our cell body and its dendrites? I mean, sure, it's going to depolarize, but do we really care if our cell and its dendrites depolarize?
No.
No. That doesn't do anything. However, some of this sodium is going to spread to the next segment of our axon. So we have a diffusion of sodium to the next segment of the axon. And when we have a positively charged ion flowing into the next segment, guess what happens to the next segment of our axon?
Gates open.
There you go. It depolarizes the next segment to threshold. After all, threshold is just a positive 10 change, and here we have this 100 millivolt change coming in. Depolarizes the next segment to threshold, and of course, what happens at threshold?
More sodium goes in?
Exactly. New voltage-gated sodium channels open, and new sodium enters the cell. So suddenly what happens is we get this opening of the voltage-gated sodium channels open. And as these voltage-gated sodium channels open, we get a huge influx of sodium entering into the cell. And when a massive amount of sodium enters into the cell, we get a big positive signal. And not just any big positive signal, but we get a positive 100 millivolt change at this next segment of our axon. Now, notice if you were watching this with the eye, what it would look like is you produced a wave, and that wave moved from one part of the axon to the next part of the axon. And did the wave get any smaller? No. Remember, we said one of the keys to this process of propagation is that it is self-strengthening. It self-propagates. Or we can say it self-strengthens. So as it travels, it stays the same size. Now, I know when we say that at first, it sounds a little silly, because how do you make a wave that stays the same size? Well, as you can see here, you're not really making one wave. Here, we've made two waves, two action potentials side by side. The same sodium that produced the first action potential is not the same sodium that produced the second action potential. So really what we've done is made two action potentials side by side. And guess what happens to all of this sodium? This massive amount of sodium that came in. That entered in this location. Is it going to stay right here where we put it? Exactly. Well, it's going to spread. Is some of it going to spread back? Oops, what happened there? Yeah. And so when it spreads back, does it suddenly open up these channels a second time and we just have an action potential that bounces back and forth? Why not? You're absolutely correct. Some sodium spreads backwards, but does not produce a second action potential there. And of course, why doesn't it? Well, it's not that it's not big enough. Again, remember, it's still a 100 millivolt change. But why, when it goes back, doesn't it produce a second action potential?
Because the gates aren't closed yet?
And yeah, don't we have a fancy name for that? A period of time where no matter what we do to the axon in that location, it can't produce a second action potential?
Refractory
It's
period.
refractory period.
Exactly. Doesn't produce a second action potential because the first area is in the refractory period. And because it's in the refractory period, it doesn't produce another action potential. However, some of that is going to also spread to the next segment. And guess what happens when it spreads to the next segment?
Makes another action potential.
Exactly. It is going to open voltage-gated sodium channels. Those voltage-gated sodium channels are going to allow massive amounts of sodium into the cell. And we are going to produce another 100 millivolt action potential. And then that's going to spread, and it's going to open up more channels. Oops, open more channels. And as it opens those more channels are going to allow in a massive amount of sodium, and we get a big action potential. And as that comes in, it's going to spread. And in this fashion, we are going to continue this process. Notice what's really happening here is we produce large local currents. Basically what is happening, and I'll use the black for this one, sodium comes in and goes to the next segment, and then sodium comes in and goes to the next segment, and sodium comes in and goes to the next segment, and sodium comes in and goes to the next segment. Notice basically what we're doing is producing a lot of local currents. And the result of all of these local currents is we continue to produce a 100 millivolt action potential that spreads down the axon and never gets smaller. So like I said, you could have an axon from here all the way to Seattle, Washington, And you could produce an action potential at one end, and it would spread all the way to Seattle, Washington. And it would never get smaller. It can go whatever distance you need it to go. All right. I have two questions for you. The first is based on this information. And again, this is the way that the neuron normally works. But one of the things that you're going to do with your PhysioX is you're going to play with and manipulate a neuron. And just out of curiosity, if you were to take an electrical stimulus and stimulate that neuron right in the middle of its axon, what do you think would happen?
It would stimulate it both ways.
Exactly. What would happen is you would produce two action potentials, and those two action potentials would both travel in the opposite directions. The axon is basically a hose for carrying sodium. You have a hose in your backyard that you use to water the garden. And the water only goes through the hose one way. But that's because one side is the part that has the coupling for the house, and the other is the side that has the coupling for the nozzle. If you chose to, if you cut a hole in the middle of your hose and stuck that hole onto the faucet coming out of your house and turned the water on, would water go out both ends of your hose?
Yes.
Yeah, because the hose's job is just to carry water. This axon's job is to carry sodium. So yeah, the reason you don't have action potentials bouncing back and forth is the refractory period. But if you stimulated it right here in the middle, sodium would spread in both directions, would depolarize both these segments because, again, they're not in their refractory period, and you get two action potentials going in both directions. The big, solid, stable signal that can go as far as we want and never get smaller. Super useful, super important. But there is one big problem. The one big problem is this takes time. This is a slow process. Right? Just think of the time it takes me to describe it. I have to reach threshold for the voltage-gated sodium channels, open those voltage-gated sodium channels, have a massive amount of sodium enter into the cell, causing a big positive signal I call an action potential. Some of that sodium then has to spread to the next segment of the axon, which will get that next segment of the axon to reach threshold. When it reaches threshold, voltage-gated sodium channels open. A massive amount of sodium comes in, giving me a big positive signal, giving me my 100 millivolt action potential. And some of that sodium has to spread to the next segment, and so on and so forth. As I mentioned, we could have an axon that goes from here to Seattle, Washington, so we can talk to grandma. Just like those ancient wired phones used to allow me to talk to grandma. When I would call grandma on that wired phone, basically what happens is my phone produces an electron. That electron moved across the wire. And how quickly do electrons move on wires? Fast, slow?
Fast.
Fast, at about the speed of light. So if you were talking on an old wired phone to grandma in Seattle, when you said hello, how long did it take for her to hear you saying hello?
Almost immediate.
Yeah, it was basically instantaneous. You say hello, she has hello, and you can have a conversation. Now, again, back in these ancient times, if instead grandma was in London, England, they had these big, huge cables that ran along the length of the ocean. And if you were trying to talk to grandma on the phone in England, all the way in England, then there'd be a tiny bit of a delay. You would say hello, a couple seconds would go by, and then she would hear you. And then she would say hello, a couple seconds would go by, and you would hear her. But still, we're talking about a couple seconds. Can you have a conversation with grandma with a couple second delay to get all the way to England? Absolutely. However, if we tried to use an axon to get our electrical signal from here to grandma in Seattle, Washington, I would say hello. It would jump onto this axon. These axons would open the sodium channels, allow sodium to come in. The sodium would spread to open more channels, to allow sodium to come in, to open more channels, to allow sodium to come in. It would take 2 days for my signal to reach grandma in Seattle, Washington. So I would say hello. 2 days later, grandma would get it. She would say hello. 2 days later, I would get it. Right? Grandma's going to be dead before we finish this conversation. Right? So the problem with this is it's a slow process. Now, if it's this terribly slow, then how the heck can we use it in our body? If it takes 2 days to get a signal from here to Seattle, Washington, then how can this possibly be an effective way for my body to communicate? If I put my hand...
For slow processes?
It is slow. It is a slow process, but if I put my hand on something hot, there you go. Allison's got it. If I put my hand on something hot, does it take 2 days for me to move my hand? No. And the reason, like Allison pointed out, is that the axon that goes from my hand to my brain isn't long enough to go from here to Seattle, Washington. Here to Seattle, Washington is hundreds of miles, right? The neurons in your cell body are not hundreds of miles long. We're talking about feet. So is there a delay? Yes, but that delay is fractions of a second. All right. There are actually some activities you can do. There's some websites you can go to where you like put your hand on the space bar and there's a red light. And then when the red turns green, you hit the space bar and it measures your reaction time. Right? People talk about reaction time. Some of that reaction time is the time for the spread of that action potential down the axon. So the way we do it is the axons in our body are much, much shorter. Now, while they're shorter, that doesn't mean we still can't improve it. Is there a way we can improve it? If only there was something we had. But... Say again?
The myelin sheath.
Myelin.
Here you go, exactly. Remember we talked about how myelin will speed up the action potential. So if we are comfortable with this one, hold on a second. Getting a tickle in my throat. If we're comfortable with propagating this action potential down an unmyelinated axon, then let's myelinate one. So any questions on this before we switch? All right, then let's go back to scratch and do the process again in a myelinated axon. We have our axon hillock. We have our axon. Let's finish this first and then we'll take our break, because then from here, this will be a good transition into the lab. This is the last lecture thing I want to talk about for today. And this won't take long. So we still have our axon hillock. And our trigger zone. And as we know, our trigger zone has those massive numbers of voltage-gated sodium and voltage-gated potassium channels. But now the key is we are going to propagate our action potential on a myelinated axon. And so we have to put our myelin sheath. Our myelin sheath, remember, is that big, huge chunk of phospholipid bilayer wrapped hundreds of times around our axon. And again, the cells, I've already asked you, so I won't do it again. The Schwann cells and the oligodendrocytes. Are the cells that produce it. And again, it's big, thick myelination, hundreds of layers of phospholipid bilayer wrapped around it. It's a big, thick layer of fat. So let's think about this. Would it make sense for the axon to have voltage-gated sodium and voltage-gated potassium channels underneath the myelin sheath? Do you think there's any sodium under the myelin sheath for it to come into the cell? Would there be any place for our potassium to go?
No.
Those? Yeah, so notice there's not going to be any point in having those there. So there are no channels underneath the myelin sheath. Now, does the myelin sheath run the entire length of the axon? Is the entire axon covered with it?
No.
No. There were gaps in between. And anybody remember what those gaps were called?
Myelin sheath gaps.
Node of Ranvier.
Yeah, the nodes of Ranvier, but again, we can just call them nodes. Absolutely. There are those nodes in between the myelin sheath. And so not surprisingly, those nodes are where you find the voltage-gated sodium and the voltage-gated potassium channels. And here's another node. And then a little bit more myelin. Excellent. All righty. So again, the process starts the same as we've seen before. A graded potential spreads to the axon hillock and reaches threshold. And of course, when our graded potential reaches the axon hillock and reaches threshold, what happens? Come on, we're almost done. Hang in there a little
Sodium
longer.
channels open.
Excellent. Our voltage-gated sodium channels open. And we have a massive influx of sodium. We get our big depolarization. And we produce our 100 millivolt action potential. Yep, you're absolutely correct. We're going to get there in a second. So again, we open these channels. Oops, nope, green. We get a massive influx of sodium. And again, we produce that big 100 millivolt change, our action potential. Excellent. Now, as Adina pointed out, once again, our sodium is going to spread. Some of it is going to spread backwards, and again, we don't care about that. But some of our sodium is going to spread here under the myelin. And it spreads under the myelin passively. I agree. Now, when it spreads passively, we have a bit of an issue here. Because again, this is a little bit of physics. Let's talk about this. When a charged particle moves, basically has two choices. that charged particle can move down the axon, or what it can do is it can stop and attract an outside ion. So our charged particle, and let's go ahead and make a quick charged particle. Come on, there we go. There is our particle. And since we're talking about sodium, we will give it a positive charge. Basically, it has two choices on what it can do inside this axon. It can spread down the axon, or what it can do, it can attract a negative ion from outside. This is a physics characteristic called capacitance. You don't necessarily need to know the word capacitance, but what you need to know is that it has the potential to attract to a negatively charged ion on the outside. And if we had a negatively charged ion here on the outside, what could happen is these two things could attract each other. And if they attracted each other, the sodium would stop moving. Now, with big, huge, thick, hundreds layers of phospholipid bilayer, is it going to be easy for a sodium to attract like a chloride outside the cell and come here? No. So with the myelin, there is little capacitance. Occurs. Instead, most of the sodium moves. Now, let's think about this, and let's go with simple numbers. 100 millivolt change, let's say that it was 100 sodium that entered into the cell right here. Are all 100 sodium going to move to the next segment? Do all 100 sodium move to the very next segment of that axon?
No.
No. You know, some of it's going to go backwards and some of it's going to move other directions. So let's say just 80 sodium move to this part. Now, are these 80 sodium just going to stay right here? No, they're going to spread. However, are all 80 of them going to spread to the next segment? Not your question. Do you think all 80 is going to go to the next segment?
No.
No, maybe only 40 do. And from there, they're going to spread. And are all 40 going to spread to the next segment? No, maybe only 20. And again, I'm totally making up these numbers, but you get the idea. Notice what happens here is that as the sodium spreads, less sodium moves. We have a fancy word for that. Basically, what happens is we say that it attenuates. This is what happens when you produce a wave in the pool. You stand in the pool, you make the big wave, and as that big wave spreads, the big wave gets smaller. And that's what happens here. As our wave spreads, our action potential attenuates. It gets smaller. Notice at this point, it started at 100, we're down to 20. We've lost 80% of the original signal. However, at this node, what do I want to do at the node? If I want to keep this process going, what do I want to do at the node?
Bring in more sodium.
I want to open some voltage-gated sodium channels. And do I need a 100 millivolt change to do that?
You just need to make up the difference.
Well, if only there was a specific voltage I needed to get to make a voltage-gated sodium channel open. Does something like that exist?
graduated.
Well, okay, but what
Gradient
to
percent.
get a voltage gated sodium channel to open, what do I have to do? I have to have the
Reach
cell
threshold.
reach threshold. Exactly. So I only need to reach threshold. And how big of a change do I need to do that? I only need a 10 millivolt change, right? So what that means is I could attenuate as much as 90%. But as long as the action potential is still strong enough to reach threshold, then I can open new voltage gated sodium channels. And so as long as I can get this cell to negative 60 millivolts here at the node, then what's going to happen is I'm going to be able to open those voltage gated sodium channels. I'm going to get a massive influx of sodium. And basically, I produce at this new location a new 100 millivolt action potential. Notice in this case, the action potential didn't stay continuous along the entire axon. Instead, what actually happened is our action potential, and they use this term, jumped from to the node. And in fact, that is what they call this propagation with a myelinated axon. They call it sultatory conduction. Sultatory means jumping. So what happens is this action potential jumped from the first location to the second. This is then going to spread down the axon passively. Because it is a passive spread, it attenuates. So it spreads passively and attenuates, but it's still big enough to reach threshold. And so what happens is we get sodium rushing in. Oops. Sodium rushing in. Voltage gated channels open. Sodium rushes in. And we get another 100 millivolt action potential. And our action potential jumps from node to node to node to node.
Is it ever possible that it doesn't reach threshold as it goes down the axon?
That is a concern, isn't it? Absolutely. So the good news is the way your body is set up, this myelin is formed in a way so that the signal is always big enough. However, theoretically, let's say, for example, I don't know, there was some type of disorder, and that disorder put a whole bunch of, oops, wrong color, put a whole bunch of cracks, even one could say multiple cracks in the myelin sheath, because what happens is our immune cells break up and destroy that myelin sheath. Then notice what would happen is you would get more capacitance. So what would happen in that case is that more ions would attract other ones. And as a result, less ions would move. You would attenuate too quickly. And if you attenuated too quickly, then when you reached there, there was the chance that you could not reach threshold. And if you could not reach threshold, your action potential would stop. But luckily, there's no such disorder that breaks up and destroys our myelin sheath, stopping us from being able to send action potentials. So Allison Scott caught my tongue in my cheek. Multiple sclerosis. That's exact. Multiple sclerosis means multiple cracks. That's exactly what that refers to. Our own immune cells destroy the myelin sheath. And when they destroy the myelin sheath, they can attenuate these action potentials too rapidly. And suddenly you don't reach threshold, and suddenly your action potential doesn't get where it wants to go. So you have visual problems, you have motor problems, right? You can have difficulty swallowing, speaking, moving your body through space, all as a result of multiple sclerosis. Remember also, we said how most of the axons in our body are myelinated, but not all of them. An example, a classic example of some axons that are not myelinated are our pain pathways. Now, this myelination, and I forgot to say it before we talked about the problem because you asked that great question. Myelination can speed up the action potential. Let's make this bigger and darker. Can speed up the action potential up to 6 times as fast. So it can make it much, much faster. However, certain pathways, and one of those pathways is your pain pathway. The axons in your pain pathway are not myelinated. Now, again, if I put my hand on something hot, you would think I would want to know that as soon as possible. So being able to send that signal to my brain 6 times faster would be really, really important. However, this system isn't guaranteed. So while it may be a little bit slower, with an unmyelinated axon, because you are always re-strengthening that signal, you have that self-propagation, you know the signal 100% of the time is going to get through. So it's better to, even if it's a teeny bit slower, it's important to make sure that pain signal gets through so you know you're in pain. So yeah, most of our axons are myelinated, but not all. And as we talked about, that multiple sclerosis affects the oligodendrocytes. So it affects myelin in the central nervous system. All right. Questions on that? All right, I got one more point for you. So we talked about how multiple sclerosis can stop that signal from going through. And hopefully nobody here is dealing with multiple sclerosis, but even a sample size this small, someone here either knows or is dealing with someone who has multiple sclerosis, knows someone who has or is dealing with it. But let's talk about something else that most of us are familiar with. Most people hopefully haven't had to deal with multiple sclerosis, but many people have had a root canal. What happens with a root canal? You go and get your drill, and does the dentist just strap you down so that you can't move, and they just go to work with that drill and you scream in pain as a result of that? No, they inject a medication. What medication?
Lidocaine.
Well, or Novocaine, right? Novocaine is what they inject. However, if you have sore muscles from that workout, you may have an ointment that has lidocaine in it. So you use that lidocaine ointment or Novocaine. There is a chemical toxin called Tetrodotoxin, TTX, which is what comes from the puffer fish. Yeah, the injection sucks, but then it makes everything super numb. Because what that injection does is that Novocaine, that lidocaine, those block the voltage-gated sodium channels. So the goal of getting that injection is they take, and I'll cheat and do this as a shaded box. They take and pick that medication over a large portion of the axon, and it blocks the voltage-gated sodium channels. So you produce an action potential, and that action potential tries to spread down the axon, but as it spreads down the axon, it can't open any more of those voltage-gated sodium channels. And if it can't open any more of those voltage-gated sodium channels, is it going to be able to get all the way down to the brain and tell you that you're feeling the pain? No. All right. Tetrodotoxin is a question on the PhysioX. Tetrodotoxin is, like I said, it comes from pufferfish. It's a very potent, long-lasting, voltage-gated sodium channel blocker. You know, we've always talked about how things, once we learn how something works, we want to use it to our advantage. Tetrodotoxin doesn't have a lot of medical uses. It's used in research a lot. I used it when I was in my research because, again, studying the development of the visual system, it could block action potentials for up to 24 hours of time. However, again, once we understand these things, we take advantage of it. Hopefully nobody here has ever enjoyed fugo. Fugo is a special type of sushi that is not legal in the United States. Right? It used to be legal in Canada. I don't think it still is. But even in Canada, when you went there, the chefs who serve it have to be recertified every 30 days. And as a patron, you have to actually sign a legal waiver saying that you waive all the rights to sue them if you die as a result of having these sushi. What these special fugo chefs would do is they would cut the pufferfish meat for your nigiri in basically with just a little bit of that tetrodotoxin. Tetrodotoxin is in a bladder, so the key is to cut it in such a way where you just get the littlest bit of it on there. So that, for instance, when you pick it up with your fingers, you get a tingling sensation on your fingers. As you put it into your mouth, you get a tingling sensation on your tongue and on your lips, but not so much tetrodotoxin that it gets into your bloodstream and ends up at some place like your diaphragm, where you no longer can control the muscle of your diaphragm and you die as a result of suffocation from eating fish. So there you go. So again, it is not something that is used lightly, very heavily regulated substance, but it is used a lot in research because it's very important that way. And even if you don't want to use medicine, right, there you are playing baseball. Back in ancient times, we had a game called baseball, and you were standing at the plate. And as you're standing at the plate, the pitcher hits you in the arm with the ball. What do you do if you get hit in the arm with a ball?
You walk automatically.
Yes, you get to go to first base. And as you go to first base, sure, you could cry, but then the pitcher wins if you do that. So you can't let him see you cry, right? You got to stare him down. But okay, let's say that, okay, yes, you cry, you stare him down. But once you get back into the locker room and no one can see you anymore, right? So you don't have to worry about being a man anymore. What do you do if someone hits you in the arm, punches you in the arm? What do? You rub it. Why do you rub it? Why do you rub it if someone punches you in the arm? Grab the person next to you right now. Find someone in your house and punch them in the arm. Right? When you do that, do it during the next break. We're about to take the break. Find someone to punch in the arm. If someone's not there during the break, go to your neighbor's house wearing a mask, punch them in the arm, and then run away. And then ask them what they do. Why do you rub it when you punch someone, when someone punches in the arm? Why do you do that? Because it feels better. It makes it feel better. Why does it make it feel better? Because when you are stimulating those tactile sensors, exactly, Haley's got it. Those tactile sensory receptors follow a similar path to the pain. And remember, as we talked about, those pain neurons are unmyelinated. So what happens is by rubbing it, that sensory stimulus confuses the pain pathway and you don't perceive the pain. Of course, as soon as you stop rubbing it, no more confusion and the pain comes back. But while you're rubbing it, you don't feel the pain because of that confusion of the stimuli. All right. We've done a pretty good job of describing these things and showing these things here with the pretty pictures that I've drawn. But again, your book's got some nice pictures that show this process as well. Notice here's our propagation on an unmyelinated axon. And don't punch your neighbor. Unmyelinated axon. Again, we're producing those local currents. We're opening up voltage-gated sodium channels, allowing sodium to rush in. That sodium rushes to the next section, depolarizes it to threshold, and we get that slow, steady, consistent propagation of our action potential. Consistent. You know the signal is going to get there, and that's a huge advantage of this process. The huge downside of this process is that it's slow. So when we can, we speed it up with our myelin. With that myelin, we can speed it up. Again, in the same way we produce an action potential, sodium rushes in, and so sodium spreads down. But now sodium has to travel a much longer distance. And so again, the key to this sultatory conduction is that we get attenuation. The signal attenuates, which again is just a fancy way of saying gets smaller. The signal attenuates, but that's okay because we had a 100 millivolt change and we just need to reach threshold. We only needed to reach -60 at the next point. And if we can do that, we open signals, allow more sodium to come in and produce another big massive action potential, which spreads. And again, much, much faster process, 5 to 6 times faster with that myelin sheath. But we just need to make sure that the signal is strong enough to keep the action potential going. And again, even though we've said it like 3 times, oh, wait, actually I lied. We talked about multiple sclerosis. We talked about toxins like Novocaine, lidocaine, and Tetrodotoxin from the pufferfish. And we've done all of that. Excellent. All right. So there you go. That is everything we need to do from a lecture standpoint for today. Yikes, we are so behind. All right, excellent. So let's go ahead and take our last break. We'll take a 15-minute break. It's 11:02, so we'll come back at 11:17. And at 11:17, what we need to do first is our histology. We will start with our histology. So have your histology lists in front of you so that when I ask the questions, you can answer them efficiently and quickly. We can work through these things. And then with whatever time we have left, we will go on to the brain anatomy. All right. All right. Questions on that? All right. I'll see you guys in 15 minutes. All righty. So we are done with our lecture for today, and it is time to move on to our lab. And again, one of the key things we need to remember that is going to help us is that there is this strong relationship between the structural classification of a neuron, the functional classification of a neuron, And someone remind me again, how many structural classifications do we have?
Two.
How many?
3.
Three structural classifications of neurons. And the relationship between the functional classifications. Someone remind me again how many functional classifications there are? 3. Excellent. And what is the third thing that there's a relationship between? Structural classification, functional classification, and location.
Location.
Excellent. So there's this relationship between the structural classification, functional classification, and location of a neuron. Excellent. And since we mentioned it, go ahead and remind me, because this will help us to make things easier. What are the 3 possible structural classifications for a neuron? How do we determine the structural? Okay, excellent. Unipolar. We determine our structural classification by how many processes come off the cell body. So we have unipolar. What else?
Bipolar, multipolar.
Bipolar and multipolar. Excellent. And what are the functional classifications of a neuron? Excellent. I see motor. What else? Excellent. Sensory and interneurons. And as we've learned, is there a relationship between those structural and functional classifications? Unipolar neurons are what kind of neurons functionally?
Multipolar.
No. Unipolar are what type of function?
Interneuron.
Neurons.
Enter.
Nope. Unipolar are not interneurons. Unipolar are what?
Sensory neurons.
Sensory neurons. Excellent. Bipolar are what?
Special sensory.
Only special.
Yeah, only special sensory. So let's cheat and do it that way so we can write special. And so then our multipolar are going to be there's a lot of background noise, so I'm going to go ahead and mute everybody, and then you can just unmute when you needed to talk. And then multipolar then can be what types?
Motor or interneurons.
Yeah, they can be interneurons or they can be motor neurons. Excellent. So we know that there's this relationship between them. So let's look at them. We've talked about these, but now let's look at some different locations. And as we look at these different locations, we can identify based on the location, that should tell us something about the structure and tell us something about the function. The first location we are going to look at is this location right here. Here is the brain. And as I mentioned, it does kind of look a little bit like a mitt. You have the big, huge cerebrum and then that little thumb of the cerebrum right there. And then way back here at the back is our cerebellum. The cerebellum is the first structure we are going to look at. And let's look at it under the microscope. First at a low magnification. Now, one of the things that should first jump out at you as you look at the cerebellum is it has these massive numbers of nooks and crannies. It has these raised ridges and then these indented grooves. Of course, we're not going to get away with terms like ridges and grooves, so we need to use the appropriate anatomical terms for these. What is the appropriate anatomical term we used for the raised ridge? If only I had my list of histology in front of me like my instructor asked me to have so that I would know this. Excellent. Folium. The raised ridge of them is what we call the folium. Folia would be the plural. Because it looks like the ruffled edges of a leaf. That's where it gets its name, folium. And what is the name we give to these indented grooves? Oops, hold on, I need that to be a color we can see.
Sulcus.
That is excellent. Sulcus being the singular, and since we did folium singular, we will do the singular of sulcus, but as Haley pointed out, the plural is sulci. So folia and sulci would be the plurals of our raised ridges and our indented grooves. All right, let's talk some more vocabulary. And again, this is a vocabulary we have already talked about. But again, I think we mentioned it briefly, so I'll cheat. And again, let's do it here. When looking at this tissue, remember we talked about our tissue, basically our nervous tissue has two parts, especially in the brain and spinal cord. We have the part that is made of the cell bodies and the dendrites. And I think I'm gonna have to make this smaller. Exactly. And the part made up of our axons. And as we know, most axons are myelinated with big layers of fat on top of them. Absolutely. So those parts that are made up of the cell bodies and the dendrites, would that be the gray matter or the white matter? What do you think?
Gray matter.
Gray matter, exactly. Our gray matter is the parts made up of the cell bodies and the dendrites. And our white matter is the part that is made up of the myelinated axons. The gray body, the gray matter, the cell bodies and the dendrites these are where we process information and make decisions. And our white matter are the pathways that carry information from one location to another. So in the brain, in the spinal cord, it is all made up of gray matter and white matter. One of the special things about the cerebellum, and again, anytime you are looking at histology, with that histology, you want those dead giveaways that are going to help you to be able to identify it quickly and immediately. One of the dead giveaways of the cerebellum is that it has two layers of gray matter. So if we look closely at this, what we can see, and let's go ahead and grab my highlighter and we'll use yellow first. It has this lighter colored outer region and the darker layered inner region. Here we have two layers of gray matter. Now, one is the chemical and one is the molecular layer. You don't need to know the names of the individual sublayers. You just need to recognize that when you see two distinct layers of gray matter, that is, and all these nooks and crannies, it is a dead giveaway you are looking at the cerebellum. And that means that this deep stuff on the inside, this is the white matter. So two layers of gray matter, one layer of white matter. And notice that the gray matter is superficial and the white matter is deep. All right. Now, I want you to notice one more thing about this white matter. Notice the white matter forms this elaborate tree-like structure. And because our anatomists love to name things, what is the name that our anatomists have given for this elaborate tree-like structure formed by the white matter in the cerebellum?
Arbor vitae.
Exactly. Arbor vitae. And what does the arbor vitae mean? Anyone know?
Live
Tree something?
Tree of life. It is the tree of life, absolutely. There are some of the people who study the cerebellum are almost fanatical in their love and passion for it. If you do a quick web search, you can actually see some people who have some massive, amazingly elaborate and incredibly beautiful arbor vitae tattoos on their arm for these beautiful pictures of the cerebellum. Actually, if we were in the classroom, there is an art student who went through the biology program many, many years ago, and she combined her two loves. And in all the classrooms in the biology building are art pictures that she's done using anatomical images and then creating art from them. And in our 430 classroom, where we usually teach this class, is a beautiful representation of her arbor vitae. It's a cerebellum with a tree and leaves and apples and stuff like that growing off it. That is really, really beautiful. So again, it's this really, really cool, elaborate, important structure. We'll talk about the function of it a little bit later when we get to the brain anatomy. But the other reason we are here is to find neurons. So here is our low magnification, gross anatomy of this histologically. So any questions on what we've got here?
Sir, can we see in this picture like the arbor vitae?
Yes, here, let me do this. Let me clear all the drawings and stuff that I have drawn. So the arbor vitae is the accumulation of the white matter. So if you notice here, deep in all of these nooks and crannies is this white matter. So all of this stuff that I'm drawing right here is the white matter. And as you can see, it looks like these elaborate branches of a tree. So all of the white matter collectively together in the cerebellum. So here's some, oops, here's some more coming down this way. It forms an elaborate branching tree-like structure. All right, so that everything that I've got colored there, all the white matter are collectively referred to as the arbor vitae. Okay.
The histology list mentions the Purkinje cell. Is that something?
Getting there next. Absolutely. So notice we're looking at this at a low magnification right now. And at the low magnification here, we really can't see the cells. However, the good thing for us is we know exactly where they're going to be, right? It's all about locations. And as it turns out, oh, I'll actually use circles. On this, even though we can't see it at the low magnification it is now, what we will find is that the cell bodies of the cells that we are interested in are going to be found on the border between the two layers of the gray matter. So between the two layers of the gray matter in all of these regions right here is where we're going to find the cells in this location. And indeed, the cells that we'll find in this location are the Purkinje cells. Now, at this magnification, we really can't see them, so we're going to increase the magnification, but I wanted to look at this in a low magnification first. So let's increase the magnification now that we know what we're looking at, and we'll be able to see those Purkinje cells. Perfect, beautiful. I love this stain. So notice, we see a folium, we see the sulcus, another folium on the other side. Notice, I'll stick with green, we can see the white matter here that is deep, white matter here that is deep. And we can see the 1, 2 layers of the gray matter. So again, even though this is a high magnification view, we instantly see those 2 layers of gray matter. We instantly know that we are looking at the cerebellum. And so then it's easy for us because all we have to do is look right here in between the 2 layers of our gray matter, and we can see all of our Purkinje cells. Here are their cell bodies. Now, we clearly have a location, cerebellum, and we know there is a relationship between structure, function, and location. So the location of our Purkinje cells is the cerebellum. Based on this location inside of the brain, what do you think the functional classification of this neuron would be? Well, how many functional classifications are there? 3. So guess, you have a 33.33% chance of getting it right. And which were the most common ones? So which one should I probably guess first?
Interneuron.
Yeah, not only do they make up 90% of the neurons, but they're the neurons that primarily make up our brain and spinal cord. So absolutely, the functional classification are interneurons, which is awesome because then that instantly tells us what our structural classification is. What is the structural classification of this neuron?
Multipolar.
Multipolar. Notice all I needed was one piece of information. All I needed to do was recognize that this was the cerebellum. And then I instantly know this is where I'm going to find my Purkinje cells. I know that they're going to be interneurons. I know they're going to be multipolar because location, structure, and function go together.
Just
Now,
clarification.
I'm sorry, go ahead.
Just to clarify, the green stripe, right down the middle, that was the white matter, correct?
No. Well, it depends. I've got 3 green stripes. So let's here, hold on. Let's be more careful. Okay. The green stripe now represents the outer surface of the cerebellum. So we have the folium here, and then a sulcus that penetrates down into it, and then the folium coming out on the other side. So basically it's 2 fingers stuck together, right? Sometimes they're separated and it's easier, but in this case, they're just together. All right. This that I've now drawn in gray, that is the white matter. Now, does it look very white in this particular stain? No, it doesn't look very white, but it's still clearly different from the tissue that surrounds it, right? The last stain showed the white matter very clearly. This shows the cell bodies very clearly. So there's different things that we can see very, very clearly on one versus the other. What we can also see very clearly is the difference in the 2 layers of the gray matter. So again, all we have to do is find those 2 layers of the gray matter on this folium, and we can see all of the Purkinje cells all the way around that folium. Now, what we don't see here is the dendrites. Remember, as I mentioned, with this multipolar interneuron, remember the Purkinje cells are the ones that we said had this big, huge, elaborate, fan-like dendritic tree. So basically, it has this massive 2-dimensional fan-like dendritic tree, and then it's going to have one axon that's going to come here and become part of the white matter. So if we were to take some stain and fill the cell in its entirety, this is what it would look like. Now, can we actually do that? Yeah, it turns out we actually can do that. So if you notice here, different stain, up close view. Notice we can't see anything else in context, but what we can see very clearly here is the 2 distinct layers of the gray matter. We know we're in the cerebellum because we've been talking about the cerebellum. I wouldn't give this to you necessarily by itself, but again, we clearly see the cell bodies here. And notice here we can start to see some of the dendrites coming off of them. Notice we don't see many axons, but how many axons does this have going through it? How many axons come off of this cell? 1. So think of it this way. If I had an apple, how many stems does an apple have on it? 1. If I were to throw that apple in there, close my eyes, and with a knife, slice it, what are the chances that I'm going to perfectly cut the apple where you're going to see the stem coming out of it? Is that going to be something that's likely to happen? No. So when we take a histology slide, the chances of you seeing the axon are very, very unlikely. But the dendrites we will see. Here we can see the processes where they're starting to come off. But again, what we're actually able to do, and I love this picture. Here, this is using a colorized fluorescent microscope. With this colorized fluorescent microscope, what we can see is all of the axons forming the white matter here in the middle. Here, we can see a Purkinje cell, and notice with this Purkinje cell, we can see its elaborate, beautiful dendritic tree that is coming off of it. Here's another one, we see this great elaborate dendritic tree. So here we can see, oh, this one's beautiful. So we can see all of these huge dendritic trees coming off of it. And then we can see some of their axons working their way this way. So they really are these big, huge fan-like cells found in here in the cerebellum. And again, 2 layers of gray matter. Gray matter is superficial. And right in between those 2 layers is where we find the Purkinje cells. And the white matter forming that arbor vitae. Now, again, it doesn't look much like the arbor vitae from this picture, but we're just looking at one folia.
Sir?
Yes.
A question about the gray matter. In this picture, which one is the gray matter? As we say, there are 2 layers. So the white, this
These
one,
are the
okay.
2 layers of the gray matter. Remember, in the cerebellum, gray matter is superficial. So this is the 2 layers of the gray matter.
So the cell body that you want identified, is that the cell body of the Purkinje cell?
Correct.
Okay.
Yep. All right. Any more questions on this location? So we've had a location, we've had a function, and we've had a structure. Location, function, structure, all hand in hand and hand in hand. Let's look at a second structure. We will talk about the anatomy of the spinal cord in great detail a little bit later. But let's talk about some quick stuff. Again, notice with this stain, you can clearly see 2 different types of material, gray matter and dark matter. Here with the gray matter in the spinal cord, where's the gray matter? Is it superficial or is it deep? No, what part looks darker as you look at it? Deep. So here the gray matter is going to be deep, and our white matter is superficial. Exact opposite of what we saw in the cerebellum. And notice that the gray matter forms this kind of butterfly shape with these big enlargements called horns. Notice also the biggest horn is this horn right here. And even though I haven't given you any anatomy of it yet, I will tell you that this biggest horn is an anterior, this is the front, gray horn. So notice on the microscope here, we can clearly see the anterior gray horn, and we have our second location, an anterior gray horn. However, if I remember correctly, when I look at my histology sheet, what kind of prep is there for this spinal cord for the first slide? Spinal cord slide is, what does it say?
A smear.
Smear. Guess how you make a spinal cord smear? Not a trick question.
You smear it?
There you go. You take a slide, you take the spinal cord, and you smear the spinal cord on the slide. Now, when you do that, is it going to look all pretty like this picture? What do you think? Do you think you'll have the perfect arrangement of the spinal cord if you smash it and rub it around on the slide? No, of course not. What you get is something that looks whoops, like this. Here, we have spread the cells around. We lose the structure, we lose the organization of it, but what it does allow us to do is it spreads out the neurons and allows us to see these neurons. And since the largest number of neurons are in the anterior gray horn, pretty much all the neurons we see here from a location, even though this is a spinal cord smear, the location of these are going to be anterior gray horn cells or neurons. So we have a location. Now, we also, because we can see them, let's be easy. What is our structural classification? Structural classification is determined by the number of processes. So let's take this cell in the bottom left. How many processes does it have?
2 or more.
Yeah, exactly. Once I hit 3, do I have to keep counting? So what is my structural classification?
Multipolar.
It is multipolar. Absolutely. So multipolar. So what do you think its functional classification is? Multipolar, we have choices. What are the 2 choices?
Motor
Motor
neurons or
or
interneurons?
Motor or interneuron, absolutely. And as it turns out, these are the ones whose axons go out to talk to our skeletal muscle cells. And if their axons go to skeletal muscle cells, what would that make their functional classification?
Motor?
And you get partial credit for that. Absolutely, motor is a good start, but remember this is going to skeletal muscle. So what kind of motor would this be?
Somatic.
Somatic motor, excellent. So here, once again, we have a location, we have a function, we have a structure. Now, again, notice the really nice thing about this smear. The really nice thing about this smear is that we can see the individual cells and their processes. We lose the organization and the anatomy, but we see these. We see the nucleus really nicely. We can see nucleoli inside them really nicely. We can see a lot of really, really good things this way. Notice one other thing as well. There are a whole bunch, use this color, of other dots that I can see here as well. There's a dot, and there's a dot, and there's a dot, and there's a dot, and there's a dot. What do you think all these dots would be? Is that just dirt that got on the slide?
Purkinje cell.
You got the right idea. They're not Purkinje cells because remember, they are Purkinje cells are just in the cerebellum. This is our spinal cord smear. But you're right, they're cells. They're nuclei. But they're not neurons. So what would that make them? There you go. Alina's got it. These are the neuroglial cells. Now, as I look at this one right here, put a big circle around this one right here, just by looking at that one nucleus, can we tell which of the 24 neuroglial cells are located in this area that might be? I've only held you responsible for 4 in the central nervous system, but there are literally dozens. And can we tell which one it is just by looking at that? No, of course not. So with anytime I point at one of these dots, just use the generic. All of these dots are neuroglial, or remember what we'd also could say is glial cells. Now, let's take an even closer look at one of these neurons. Here is a nice, tight, up-close view. Again, this is clearly a multipolar neuron. This is our anterior gray horn. But the nice thing about this is we can see some other details. Again, we can clearly see the nucleus and some nucleoli in there. But notice also there's all of this dark stained material out here in the cell body. Any idea what all of this dark stained material might be?
Nissel bodies?
Exactly. These are the Nissel bodies. And what's the other name for the Nissel bodies?
Rough endoplasmic?
Yeah, it's the rough endoplasmic reticulum, absolutely. And notice one more thing as well. Here, I'll use a really fine highlighter for this one. Let's use orange. Notice as we look in the processes, we can see all of these linear structures coming out into the processes. They're what give them the their stability, their strength, allow for transportation. Any idea what these linear structures going out into the processes might be?
Neurofilaments.
Neurofilaments, right? They're part of the cytoskeleton. Now, I count a half dozen processes coming off of this one cell, right? This one neuron. One of those is going to be an axon, and all the rest are going to be dendrites. Can we tell which is which? Let me rephrase that. Is it possible to tell which of these processes coming off is the axon? Yes, it is possible. Do I expect you to be able to do it? No. So notice on your list, it doesn't say axon or dendrites, it says processes. So in this case, we see that there are many processes coming off of it. We don't have to worry about which one is the axon and which ones are the dendrites. We'll just use the generic term processes for this so that you don't have to worry about distinguishing them. Okay? So our neuron has many processes, and as you can see, the processes are filled with neurofilaments, giving them their structure and allowing for transportation. So there is our second location and our second type of functional cells. Right? We've seen motor, we've seen interneurons. And notice both were multipolar. But are all neurons multipolar? No. So let's see another one. Questions on this before we switch gears? Let's look at a different location associated with the spinal cord. As I mentioned earlier, and again, we'll talk about all the anatomy of the spinal cord, so if you're not familiar with these things, this is okay. As I mentioned, this is anterior. And is there another term we could use for anterior? Completely interchangeable with anterior?
Dorsal.
Ventral.
Dorsal, ventral.
Ventral.
But you are correct in that dorsal and posterior go hand in hand. If you will notice, there are these bundles of axons that come off of the spinal cord. Not surprisingly, this one on the back is called the dorsal root. And this one on the front is called the ventral root. Now, could you call them anterior root and posterior root? Absolutely. Remember, these terms are interchangeable. However, if you notice on the dorsal root, there is a big, huge enlargement. This big, huge enlargement is a collection of cell bodies. But notice this collection of cell bodies is not in the brain, not in the spinal cord. So what is the fancy name we give to a collection of cell bodies that is outside the central nervous system, that is in the peripheral nervous system? What do we call a collection of cell bodies?
Plexus?
Close. Plexus is axons and ganglion forming a big elaborate network. But what do we call a collection of cell bodies?
Tracks?
No, tracks are the axons. Starts with ganglion.
Root.
No. How about ganglion? Ganglion. A ganglion is a collection of cell bodies in the peripheral nervous system. So So a collection of cell bodies in the peripheral nervous system is called a ganglion. Is there only one ganglion in the entire body? No. So this one that happens to be on the dorsal root, guess what we call this location that happens to be on the this collection of cell bodies that happens to be located on the dorsal root?
Dorsal root ganglia.
There you go. See how easy that is? And again, ganglia is plural. We're just looking at one, so we'll go with ganglion. But if you use ganglia on the exam, I wouldn't mark you off for it. Excellent. So now we have a third location, a dorsal root ganglion. Now that we have that location and we know what we're looking at, let's look at it up close. Here's a pretty good up close view. Here we see the axons coming into it, and here we start to see the cell bodies. But let's take an even closer look at the cell bodies. Again, this by itself, without working it up to it, doesn't make a whole lot of sense. But now we're going to see how this is going to be so super easy. Because I see plenty of cell bodies. Here's a cell body. Here's a cell body. Here's a cell body. Here's one. Here's one. Here's one. Here's one. Here's one. How many cell bodies do you see on this image? Okay, you don't have to actually count. There are, but definitely more than 20, a lot. And with all the cell bodies here, how many processes do you see? Do you see any processes coming off of any of these cell bodies? None.
No.
Does that mean they have none? No. So what do you think the structural classification of all these neurons are going to be?
Uni?
Exactly. It's that old pesky apple with a stem, right? What are the chances you're going to cut it perfectly where you're going to see the stem on the apple? Not very likely. And the same thing's happening here. So notice our location of the dorsal root ganglion is going to be where we find the unipolar neurons. So notice it works both ways. If I were to show you this image and you were to recognize that all of these neurons are unipolar, then what must your location be?
Spinal cord?
Nope. If you're not sure, I actually wrote it on the board.
Dorsal?
Dorsal root ganglion,
Yeah.
right? The dorsal root ganglion is going to be the only place you're going to see unipolar neurons. So if you see unipolar neurons, where must you be?
In the dorsal root ganglion.
In the dorsal root ganglion, exactly. Location, structure, function go hand in hand in hand. The only place you see unipolar neurons are in the dorsal root ganglion. So if you see unipolar neurons, you know you're in the dorsal root ganglion. If I tell you you're in the dorsal root ganglion, what type of neurons must be there? They must be unipolar. And if they're unipolar, what is their function?
Sensory.
There you go. Once again, location, structure, function. Sensory neurons are unipolar neurons, and they're found in the dorsal root ganglion. So if I give you one of those three pieces of information, you have the other two. Now, I want you to notice one other interesting thing. Well, actually, I lied. Two other interesting things about these unipolar neurons. The first is while I don't see any of their axons, what I do see are all of these dark nuclei of cells wrapped around the periphery of them. Now, what, of course, would the generic term of these cells forming a halo around these be?
Satellite?
Well, okay, the generic term would be neuroglial cells, but you're absolutely right. the specific neuroglial cells that we find here in the dorsal root ganglion are the satellite cells. Remember, dorsal root ganglia is in the peripheral nervous system. Peripheral nervous system have satellite neuroglial cells. So that's the other dead giveaway. You see all these satellite cells, you see these clusters of cells forming halos around these cell bodies. And again, it's a dead giveaway. You are in the dorsal root ganglion looking at unipolar neurons that are sensory in function. Now, one last thing. Notice some of these cells are very light in color. Some of these cells are more medium in color, and some of these cells are really dark in color. As it turns out, these particular neurons, when they're metabolically active, they produce this undigestible fat that accumulates inside the cell. There have been many studies on it, and it doesn't appear to serve any function. It's not harmful, it's not helpful. It's more just a sign of use or a sign of age, kind of like the liver spots on grandpa, right? Grandpa's got liver spots and it doesn't do anything other than make him look old. And that's kind of what happens here. Any idea what you might call this dark stained lipid, undigestible lipid fat found inside of these cells?
Lipofuscin?
There you go. If only I had a list of terms that I was responsible for on my histology in front of me, I could read the word lipofuscin off of my list and see that that lipofuscin is this undigestible fat that forms this dark pigmentation to our unipolar neurons. All right. Questions on that?
So what did you call the last one, the dark stain undigestible fats you said, sir?
It's lipofuscin, which again is on your histology list. So
Lipofuscin.
this one here has a large amount of lipofuscin in it. This one has a moderate amount of lipofuscin in it. This one has almost no lipofuscin in it. So again, just the different colorations of the stain because of the different material that they have inside of them. All right. Questions on that? All right. One more location. The bestest, most importantest location in the human body. Stare in wonder, revel in the majesty that is the human eye. The truly greatest organ ever invented on the history of the planet. All right, truly glorious in all of its majesty. Now, what we are interested in, excellent, thank you, is this structure back up here. Wait, hold on. This structure back here, this dark pigmented structure that we see back here is our retina. And that is what we're going to do next. We're going to come up here and take an up close view of the human retina. Excellent. And this is still oriented the same way. So the front of the eye is over here on the right. So light comes in this direction. Let me do that again. Light comes into the eye in this direction. Now, there are four important things that you see here when you're looking at this. The first thing that you should see is in the back of our eye, there is this very dark pigmented layer. This is known as the pigmented epithelium. This pigmented epithelium is basically what allows us to see clearly during the day. We are primarily diurnal animals, meaning that we are active during the day. And during the day, there's more than enough light for us to be able to see. There's actually too much light. So what this dark pigmented epithelium does is it allows us to absorb most of the light that comes into the eye, allowing us to focus more clearly, right? When you buy that brand new 4K TV, do you take the brightness and turn it up as high as it possibly can be so you get as much light coming out of it as possible? Is that the best way to watch TV? No, right? If you do that, you're going to lose contrast, right? You want enough brightness so you can see clearly, but you still want to see sharp images. This allows us to see sharp images. But that's because we're diurnal. What about your cat? What have you ever noticed about your cat, especially at night? Aside from the fact that they're evil and they'll torture you. Yeah, they're crazy, right? With even a little bit of dim light in the house, what happens to the cat's eye?
Their pupil gets huge.
Their pupil gets huge, but it also, you get light reflecting off of their eyes, right? Their eyes kind of glow in the dark. The reason for that is they're nocturnal creatures. They actually have a reflective. Yeah, they have a reflective layer. They have a reflective layer on the posterior part of the eye that bounces light off of it, amplifying the light, allowing them to see so much more clearly at night. Deer have this as well. Deer are more active at dusk and dawn, so they also have this reflective layer called the tapetum, which is great for that deer until you're driving at night and it's trying to cross the street. Your headlights hit that deer in the eye, it bounces off that reflective layer, and it actually photo stuns the deer. And so what does the deer do? Stands there frozen in place because of that reflection of the light. So this dark pigmented layer on the back is what allows us to see during the day. But notice the other thing we have here are 3 layers of cells. This most superficial layer.
So what's the name of this layer we talk about a lot?
Pigmented epithelium.
Pigmented epithelium. Okay, that's it.
The most superficial cells are the retinal ganglion cells. Their job is to send information to the brain. Their axons form our optic nerve. All right, and we have over 1 million of those in each eye, taking this information and sending it. This deepest layer right here are the photoreceptors. These photoreceptors are what receive the light. And they form,
white.
I'm doing that on purpose, the action potential. These form the action potentials that are going to, no, I wanted it to be white because I wanted it to show up on the image. Can you see it now?
Yes, thanks.
Excellent. So, now this one came off the screen a little bit, so let's do that. There we go. Excellent. So here we have our photoreceptors. Here we have our retinal ganglion cells. What we need is a way to get information from the photoreceptors to the retinal ganglion cells. And to do that, it would be really convenient if we had a cell that had a single dendrite that could receive lots of information from lots of these photoreceptors, and then a single axon, which would allow it to communicate with the retinal ganglion cells. So this center layer of cells in the center of our retina in our eye, guess what type of neurons these are?
Bipolar?
Exactly. These are our bipolar neurons. Their job is to take the information from the photoreceptors and give it to the retinal ganglion cells. So notice, once again, we have a location, and that location is the retina. We have a structural classification. What is our structural classification?
Bipolar.
Bipolar. And what is the function?
Sensory.
Yep, but remember, special sensory. Right, remember, these bipolar neurons are only found in special sensory. Those are places like the retina of the eye, like in the ears for hearing, in the nose for smelling, right? The olfactory epithelium, places like that. So once again, we have a location, we have a structure, we have a function. Questions on that? Taste 2.
So, sir, we mentioned at the beginning that in the retina, we have 4 important things to see. 4 things.
Yes. Pigmented epithelium,
right.
and 3 layers of cells.
Okay.
All right. Questions on that?
Yeah, after like when we start with the superficial, the most superficial cells, which is retina ganglion. So the other layer is the photoreceptor. And what is the third layer? It's a single.
So again, well, let's be careful. If you are going from superficial to deep,
right,
you have the retinal ganglion cells.
Right.
So the retinal ganglion cells. Then you have the bipolar cells. And then you have the photoreceptors.
Okay.
And see, now that doesn't work because they're dark, but you get the idea. So yeah, from superficial to deep, that is the way light travels, and it has to go through all 3 of those layers to get to the photoreceptors. All right. Yeah. So again, location, structure, function, hand in hand when we are in our nervous tissue. And that's the good thing about this. The good thing about this is if you recognize that this is the retina of this image, then you know all the answers to the questions. You know these are going to be bipolar neurons. They're going to be special sensory. If you can recognize that you're in the dorsal root ganglion, you know they're going to be unipolar. You know they're going to be regular sensory, right? The cerebellum, you know it's going to be multipolar. It's going to be an interneuron. And it works the other way as well. If I tell you I'm holding in my hand a unipolar neuron, where must that unipolar neuron have come from? Where do you find your unipolar neurons?
Dorsal root ganglion.
Dorsal root ganglion. There you go. All right. So that is going to be one of your big jobs on this exam, to start to look at and understand the relationships between structural classification, functional classification, and locations. So as we learn more and more locations, you are going to learn more and more neurons, where they are, what they do.
And do we need to sir, draw some on these histology slides or histology handout? Do we need to draw the... So
again, I provide this handout for you as a study tool. You had to turn in the first one because on the first one, people didn't appreciate how important histology was. So it was an important way to show students that taking the time to do the histology is going to be necessary to help you to be successful. Do I need to wave that carrot in front of you to get you to learn your histology at this point? Or at this point in the class, should you know how important histology is and that you need to put time and effort into it? At this point, you should know. So it is your study guide to remind you, just like the first one was a study guide, but no, I'm not going to bother to collect it. At this point, you guys should be sophisticated students. If you don't want to put that time and effort into your histology, then guess what? This is college and you're adults and you don't need to. But are you likely to be successful on the exam if you're not going to put the time and effort into the histology? Probably not. Yes, I agree with Haley. How much time you put in the histology does show up in your grade. That's probably one of the problems with histology. as we go through this material, I always try to give you guys tricks and cheats and ways to remember these things, good mnemonics, dead giveaways to help you with these things. And there are definitely some of those, but some of this is just brute force memorization. The more time you spend with the histology, the more familiar you'll be and the more comfortable you'll be. And it's not a waste of time. When you get to 431, we're going to be doing histology as well. So the histology doesn't go away. So it's important to learn to love it now. All right. All right. We did not get to, all right. So hold on. Where are we? We still did not get to any brain anatomy today, but okay, so here's what's going to happen. Wednesday's lecture is going to be relatively short. We don't have a lot of stuff to go over, and a lot of it is kind of summing up information we've already kind of talked about, giving some labels and names to things. So the lecture won't be very long, but that means we'll have a lot of time to start focusing on the anatomy. We haven't started the anatomy yet, but we're going to start working on that anatomy together. I have some unlabeled pictures for you in the module that you can use, similar to the ones that I'm going to be showing you. They're ones basically from your textbook. So you have a textbook, you have that. You have your list that we'll be going through. So we'll be going through that list and try to get through as much of it as we can on Wednesday. And then what we don't get through on Wednesday, we will finish up on Monday, the following Monday when we come back. In fact, we'll do the lab first, then the lecture, and then hopefully cranial nerves. So that'll be the game plan. So yep, busy couple days. Wednesday and Monday are going to be busy, busy days. All right. Questions on any of that? All right. I will see you guys on Wednesday. So remember, we will be starting with a 5-point daily quiz. So again, please be here. Again, it's going to be an important day. We're covering a lot of material. Yes, there was a question.
Yeah, the question is about the final cumulative exam.
Yes.
If somebody takes the 5th one, like the coming exam, which is on 9th, and the student is not willing to take the cumulative exam, so what will be like? Is it optional or?
No, well, again, this is college, you're adults. You don't have to take it if you want, but it counts. It counts towards your grade, absolutely. So if you don't take the final exam, you will get a 0 for the final exam. The final exam counts as a grade on its own. It is a 100-point assignment. It is a 100-point grade that counts on its own. It also can replace your lowest lecture score. It doesn't have to. If your lowest lecture score is an 80 and you get a 79 on the final, I'm not going to replace your 80 with a 79, but it still counts as a 79 on its own. So it counts as a grade on its own. Whether you want to take it or not is completely up to you. It's a beautiful thing about college. You're all adults. You're paying to be here. So I think you should be motivated, but nobody's required to do anything they don't want to do.
No, what I'm saying, what my question is like, does it affect, like, as you said, that it's going to replace one of our lowest
But see, that's
exams?
an additional thing that it can do. It counts on its grade. It counts as a grade on its own, no matter what.
Okay.
So if you have banked enough points in this class where you can afford to get a 0 out of 100 on the final exam, then you don't have to take the final exam. It hasn't happened yet, although I did have a student who was doing well enough where I think he only needed a 56 on the final. And so he basically, because again, this was when we were on campus, he didn't bother studying for it and was able to focus on all of his other classes because he figured based on what he knew, he could do better than 60%. And he did. I think he got like a 72 or something like that. And so he was able to maintain his grade. But even he had the top grade on all of the exams. Even he still had to take it to maintain his A. So you need to take the final.
Thank you, sir.
Well, you should take the final. You're not required. Again, college, adults. But if you want a passing grade, I would encourage you to take the final.
Sure. Thank you, sir.
All righty. Great question. Any others? Yeah, I want to make sure that's clear. Again, it can replace your lowest lecture score, but it definitely counts as a grade on its own. So make sure you prepare for that. And the good news is you'll have a whole week to prepare. So I wouldn't spend too much time between now and then. We have so much nervous system stuff to cover. Focus on the nervous system, and then that whole week you have off, you can prepare for the final.
And the final exam is all multiple choice, right?
All multiple choice. That is correct.
Thank you.
All righty. You guys have a good day, and I will see you on Wednesday.